Please subscribe to support the channel. Light speed, about 300,000 kilometers per second, is the fastest anything in the universe can move, yet humanity is nowhere near achieving it. We can launch rockets beyond our atmosphere and send probes past the edge of our solar system, but compared to light, we barely crawl through space. Even our fastest spacecraft would take thousands of years just to reach the nearest star. Still, the idea of moving at light speed fascinates us because it promises instant journeys across galaxies, new worlds within reach, and a glimpse of a universe without limits. But as we'll discover, the same physics that make light so extraordinary also make it an unbreakable barrier for anything with mass, including us. The speed of light is more than just a large number. It's one of the most profound constants in all of physics, a value so fundamental that it shapes the very structure of reality itself. Light travels through the vacuum of space at roughly 299,792 kilometers per second, or about 186,000 miles per second. That means that in just 1 second, a beam of light can circle the Earth 7.5 times. In human terms, it's impossible to comprehend that kind of velocity. It's so fast that when you turn on a light in a room, the photons reach your eyes almost instantaneously. Yet, in the grand scale of the cosmos, even light takes time. The sunlight warming your face left the sun about 8 minutes ago. And when you look at the nearest star system, Alpha Centauri, you're seeing it as it appeared over 4 years in the past. Every glance at the night sky is a look back in time. What makes light speed so special isn't just that it's fast, it's that, according to the laws of nature, nothing can go faster. This isn't a technological limitation, it's a physical one. The universe itself enforces this rule as a cosmic speed limit built into the equations that govern space and time. In fact, the speed of light is so fundamental that it's represented by the letter c in Einstein's famous equation, E equals mc squared, where it ties together energy and mass in a way that reveals their deep connection. Light speed is the conversion factor between the energy locked inside matter and the energy it could release if that matter were converted completely. It's the yardstick that defines how fast cause can become effect, how fast information can move, and how quickly events can influence one another across space. To truly grasp why this limit exists, we have to think of space and time not as separate things, but as a single fabric called space-time. Imagine reality as a 4-dimensional continuum, 3 dimensions of space woven together with 1 dimension of time. Every object that exists, from planets to particles, moves through this fabric at a constant combined rate. If you're standing still in space, you're moving through time quickly. If you're moving quickly through space, you're moving more slowly through time. Light, however, doesn't age at all. It moves entirely through space, not time, traveling at the universe's maximum possible velocity. For light, the concept of time essentially freezes. It experiences no before or after. From the photon's perspective, it's created and absorbed in the same instant. That's how extreme light speed truly is. It doesn't just change distance, it alters the very experience of existence itself. But how do we know this limit is unbreakable? The key lies in the fundamental constants of physics. The vacuum of space has properties, permittivity and permeability, that determine how electromagnetic waves, including light, propagate through it. When you calculate the speed based on those constants, you get the exact value of c. In other words, light speed isn't just about the motion of particles, it's about the electromagnetic nature of space itself. It's not something that can be outpaced because it's woven into the universe's structure. When physicists say nothing can move faster than light, they don't mean we simply haven't built something powerful enough yet. They mean that the very geometry of the universe forbids it. If an object with mass were to reach or exceed that speed, the equations describing energy and momentum would stop making sense. They would demand infinite energy, infinite mass, and infinite curvature of spacetime. It would be like dividing by 0, not just difficult, but meaningless. Another remarkable thing about the speed of light is that it remains the same for all observers, no matter how fast they're moving. This discovery, one of Einstein's greatest insights, overturns centuries of classical physics. If you're riding on a train moving close to light speed and you shine a flashlight forward, the beam of light won't move away from you faster than it does for someone standing still on the ground. Both of you will measure its speed as the same constant, 299,792 kilometers per second. This invariance is the cornerstone of special relativity, and it's what makes light speed such a strange and absolute boundary. Every attempt to get close to that speed leads to bizarre consequences. Clocks tick slower, distances shrink, and energy demands soar. These effects aren't illusions, they're real distortions in space-time. Nature enforces this cosmic rule not with a barrier of steel, but with the bending of time and the warping of space. As something moves faster and faster, it doesn't just get closer to the speed of light, it begins to experience reality differently. If light is the universe's ultimate messenger, it's also its gatekeeper. It dictates how far we can see, how quickly we can send information, and how soon we can reach the stars. Even our most advanced technologies, from GPS satellites to particle accelerators, rely on our precise understanding of the speed. Without it, our entire framework for measuring and predicting the universe would collapse. In a sense, the speed of light defines what's possible. It's the upper limit of motion, the maximum flow of causality, and the rhythm by which the universe itself ticks. Every photon racing across the cosmos reminds us of this fundamental truth. There is a ceiling to motion, and it is absolute. But that ceiling is where Einstein's revelations begin to take hold. To understand why light speed cannot be surpassed and what happens as we try to approach it, we need to explore the theory that revolutionized our understanding of reality. It's the theory that united space and time, rewrote the laws of motion, and revealed the strange, elastic nature of the cosmos. It's the work that explains why light speed is not just fast, but final. At the dawn of the 20th century, physics stood at a crossroads. For centuries, scientists believed space and time were fixed, that the universe operated like a grand clock, with absolute positions and absolute moments ticking in perfect unison. This worldview, shaped by Newtonian mechanics, suggested that time flowed the same for everyone and everywhere, and that motion could be measured against a single, unmoving backdrop. But in 1905, a young patent clerk in Switzerland named Albert Einstein shattered that notion forever. His theory of special relativity revealed that space and time are not rigid and separate entities, but fluid and interconnected aspects of a single, unified reality, space-time. This realization didn't just adjust our understanding of the universe, it redefined it. Einstein began with a radical, yet deceptively simple idea. The laws of physics are the same for all observers, regardless of their motion, and the speed of light is constant for everyone, no matter how fast they're moving. These two postulates were revolutionary because they directly contradicted classical intuition. In everyday experience, if you throw a ball forward from a moving train, an observer standing on the platform would see the ball's speed as the train's speed plus the ball's throw. But light doesn't behave like that. If you shine a beam of light from the front of a spaceship moving at half the speed of light, that beam doesn't travel at 1.5 times light speed. To both you on the ship and an observer standing still in space, the beam still moves at exactly 299,792 kilometers per second. No faster, no slower. Always the same. That simple fact has staggering consequences. To make the speed of light the same for everyone, the universe has to bend its own rules. It has to stretch time, shrink space, and alter the very sequence of events. What Einstein uncovered is that time and space adjust themselves depending on how fast you move. They're not fixed backgrounds, but dynamic quantities that conspire to keep light speed constant. This is the essence of relativity. The idea that motion through space and motion through time are intertwined, and that increasing one decreases the other. To visualize this, imagine space-time as a four-dimensional fabric. You are always moving through it, even when standing still. At rest, all your motion is through the time dimension. You're aging, seconds are passing, your clock is ticking. But as you begin to move faster through space, your motion through time slows down. If you could somehow reach the speed of light, all your movement through time would stop completely. From your perspective, time would freeze. That's why photons, which always move at light speed, experience no time at all between emission and absorption. For them, the universe happens in an instant. Einstein's theory fundamentally links space, time, and speed in a single equation that describes how they transform relative to one another. When you approach light speed, time slows down for you, compared to someone standing still, an effect known as time dilation. Distances in the direction of travel contract, an effect called length contraction, and your mass, or more precisely your energy, increases. All of these changes are not illusions. They are measurable physical effects confirmed by countless experiments. One of the most elegant expressions of this relationship is the equation E=mc². This is not just a statement about nuclear energy. It is a statement about the structure of reality. It tells us that energy and mass are interchangeable, two sides of the same coin. As an object's speed increases, its energy increases, and because energy and mass are equivalent, it's as if the object becomes more massive. The faster you go, the more energy you need to continue accelerating. This is the first glimpse into why reaching light speed is impossible for anything with mass, because the closer you get, the harder the universe pushes back. Special relativity also rewrote how we think about simultaneity, the idea of now. In the Newtonian world, if two events happen at the same time in one place, they happen at the same time everywhere. But relativity says otherwise. Two events that appear simultaneous to one observer might happen at different times for another observer moving at a different speed. Time is not universal, it's relative. Each person, each object carries their own private flow of time, depending on their motion through space-time. These concepts may sound abstract, but they have practical, measurable consequences. GPS satellites orbiting Earth must account for both special relativity and general relativity, another of Einstein's breakthroughs, that incorporate gravity to provide accurate positioning. Without these corrections, your phone's navigation system would drift by several kilometers each day. Time dilation has been observed in the decay rates of high-speed particles, in atomic clocks flown around the world, and in the precise synchronization of satellite networks. The universe is constantly proving Einstein right. Yet what's most remarkable is that all of this stems from one idea, that the speed of light is absolute, and everything else must adapt. Space can stretch, time can warp, and energy can grow, but light speed remains the same. Einstein's theory didn't just describe the cosmos, it revealed its underlying symmetry, its deep logic. It showed that what we perceive as motion is really a trade-off between our journey through space and our journey through time. But if space and time are flexible, if mass and energy are two forms of the same thing, then what happens when we try to push that system to its extreme? What happens when an object with mass begins to move faster and faster, drawing nearer to the ultimate speed limit? That question leads us to one of the strangest consequences of relativity, the idea that an object's mass effectively increases as its speed rises. The faster you go, the harder it becomes to keep accelerating, until the required energy becomes infinite. This is not just a theoretical curiosity, it's the very mechanism by which the universe prevents us from ever reaching light speed. As Einstein's theory of relativity unfolded, it revealed something both astonishing and deeply counterintuitive. The faster an object moves, the heavier it becomes, not in the traditional sense of gaining more matter, but in how the universe perceives and responds to its motion. This concept, often referred to as relativistic mass increase, is one of the most mind-bending ideas in physics, and it lies at the heart of why light speed remains unattainable for anything that has mass. Imagine you're in deep space, far from any gravity, piloting a sleek, futuristic spacecraft. You fire the engines and start accelerating. At first, you pick up speed quickly. Every burst of thrust adds noticeable velocity. But as you continue to accelerate, something strange begins to happen. The more energy you pour into your engines, the less effect it has. Your spacecraft still speeds up, but by smaller and smaller amounts. It's as though the universe itself is pushing back. What's actually happening is that as your velocity increases, your relativistic mass, the amount of inertia you carry, also increases. You're effectively getting heavier in a relativistic sense. The mathematics behind this effect can be summarized in a deceptively simple equation. As your velocity approaches the speed of light, v, your relativistic mass becomes your rest mass divided by the square root of 1 minus v squared over c squared. The closer v gets to c, the smaller that denominator becomes, which makes the total mass grow toward infinity. If you could somehow reach light speed, that denominator would hit 0, and dividing by 0 would yield an infinite result. In plain terms, it would take infinite energy to accelerate a massive object to the speed of light. Infinite energy isn't just a big number, it's a physical impossibility. The laws of thermodynamics, the conservation of energy, and the structure of space-time itself all converge to make it unattainable. This isn't just theoretical. We've seen the effects of relativistic mass increase directly in high-energy physics experiments. In massive particle accelerators like the Large Hadron Collider, scientists routinely accelerate subatomic particles, such as protons, close to light speed. These particles reach over 99.999999% of the speed of light, but never actually hit 100%. Each tiny increment closer to that ultimate velocity demands exponentially more energy. By the time a proton is moving that fast, it's carrying thousands of times more energy than it had at rest. Its behavior matches Einstein's equations perfectly. It's heavier in motion, harder to accelerate, and governed entirely by relativity's strange geometry. This mass increase isn't something you could ever feel in a human-scale setting because we live so far below relativistic speeds. Driving your car, flying a jet, or even orbiting Earth barely nudges your speed relative to light. But in the realm of high-speed particles, where velocities flirt with light's edge, these effects dominate. The universe enforces its limits smoothly but firmly. The closer you get to light speed, the more resistant you become to further acceleration. This phenomenon can also be understood in terms of momentum. In classical Newtonian physics, momentum is simply mass times velocity. But in relativity, momentum depends on both velocity and this increasing relativistic mass. That means that even though your velocity might not be changing much, your momentum continues to grow dramatically as you pour in more energy. At near light speeds, it's like trying to push a wall. You can keep applying force, but the result becomes almost negligible. The energy doesn't vanish, though. Instead, it goes into distorting space-time itself and into increasing your energy equivalence. The universe is in a sense saying, no more speed, only more energy. This principle explains why photons, particles of light, are unique. They have no rest mass at all, which means they don't need infinite energy to travel at light speed. They simply exist at that limit by their very nature. Everything with mass, however small, must forever stay below it. Even an electron, one of the lightest particles we know, would require unbounded energy to cross that threshold. If we were to think of the universe as a racetrack, light is the one participant that starts at full speed, always at sea, always massless. Every other contestant starts with mass and therefore with inertia. And no matter how much energy they add, they can only approach, never match that ultimate velocity. The finish line, light speed, is always just out of reach, receding infinitely as you chase it. It's worth noting that the term mass increase is somewhat outdated in modern physics. Scientists today often prefer to say that the object's energy increases rather than its mass, since energy and mass are interchangeable. The object's rest mass, its mass when stationary, remains constant. What changes is how its energy and momentum interact with space-time. The practical result, however, is the same. The faster you move, the harder it becomes to keep accelerating. This natural resistance built into the structure of space-time acts as the universe's way of protecting its own order. It ensures that no matter how advanced our technology becomes, we can't cheat the fundamental rules that connect energy, motion, and the fabric of reality itself. Relativity doesn't merely slow us down, it defines what speed even means. And as this relativistic weight increases, the consequences compound. Every additional bit of speed requires exponentially more energy, creating a feedback loop of demand that spirals toward the infinite. It's this escalating energy requirement that truly seals the deal on why we'll never reach light speed. The universe doesn't simply make it hard, it makes it impossible. Yet this very impossibility leads us to an even deeper question. If mass increases and energy demands explode, how much energy would it actually take to push a massive object, like a spaceship or even a human, to light speed? The answer, as Einstein's equations reveal, is both awe-inspiring and humbling. It's a number so vast that even the entire energy output of all the stars in the Milky Way couldn't supply it.
This realization takes us to the next step in our journey, the skyrocketing energy requirements of near-light-speed travel and the ultimate wall that infinite energy presents.
As an object accelerates through space, it's easy to imagine that all it takes to keep speeding up is more fuel, more thrust, or a stronger engine. But according to Einstein's theory of relativity, the universe doesn't play by those intuitive rules. Every time an object with mass moves faster, it doesn't just gain speed. It gains energy in a way that bends the normal relationship between force and motion. This relationship starts out gentle, predictable, and manageable at everyday velocities. But as that speed creeps closer and closer to the cosmic speed limit, the speed of light, the rules shift. Energy requirements stop rising linearly and begin to rise exponentially. The curve doesn't just get steep, it shoots upward toward infinity. This is the ultimate brick wall of physics, and it's why no amount of technology, no rocket, and no futuristic engine can ever reach or exceed light speed. In classical physics, you can keep accelerating something as long as you keep adding energy. Double the energy, double the speed. Simple and intuitive. But in relativity, that simple relationship collapses. The energy you input doesn't just go into increasing the object's velocity, it also increases its relativistic mass, which in turn increases the energy required for further acceleration. It's a self-reinforcing cycle. More energy makes the object harder to accelerate, which requires more energy still. The closer it gets to light speed, the more extreme this effect becomes, until the numbers explode beyond imagination. Let's try to visualize this with a practical analogy. Imagine you're pushing a shopping cart in a supermarket. At first, it's easy. A small push gets it moving, and a few more pushes make it glide faster down the aisle. But now imagine that with every push, the cart becomes a little heavier. The faster you get it going, the more it resists further acceleration. Soon, even your strongest shove barely moves it. Keep adding more force, and you realize that it's not just heavy, it's becoming infinitely massive. You can keep straining, but you'll never make it reach an infinite speed, because that final burst would require infinite energy. That's precisely how the universe behaves with anything approaching light speed. The relativistic energy equation shows exactly how this plays out. The total energy of a moving object equals its rest energy plus its kinetic energy. E equals mc squared over the square root of 1 minus v squared over c squared. At low speeds, this formula reduces to the familiar classical expression for kinetic energy. But as velocity v approaches c, the denominator, the square root term, approaches 0. Divide by a number approaching 0, and the result shoots toward infinity. That means that no matter how much energy you supply, you can never reach light speed because you can never have infinite energy. Consider what this means in practice. A spacecraft traveling at 10% of light speed would need an enormous amount of energy, something like the total annual energy consumption of the entire human civilization. At 50% of light speed, the energy required would be comparable to converting whole planets into pure energy through matter-antimatter annihilation. Push further to 90% of light speed, and the requirements would dwarf even the total energy output of our sun. But the jump from 99% to 99.9999% of light speed would demand so much energy that it exceeds what all the stars in our galaxy could produce in their lifetimes. Even for the smallest particles, these demands are staggering. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, can accelerate protons to within a fraction of a percent of light speed. To do this, it uses superconducting magnets and consumes enough electricity to power a small city. Yet those protons, despite being subatomic and almost massless, still cannot reach 100% of light speed. Every additional decimal place closer to that limit costs exponentially more energy. For a spacecraft carrying humans, with a mass of tens or hundreds of tons, the required energy becomes incomprehensible. It's not just a question of technological limitation, it's a fundamental wall in the laws of nature. The universe's energy bookkeeping is strict and unforgiving. Every bit of energy we can generate, from chemical combustion to nuclear fusion, is finite. Even if we harnessed antimatter, the most energy-dense fuel imaginable, we would still be billions upon billions of times short of what's needed to push a small mass, even close to light speed. Antimatter annihilation converts 100% of mass into energy, unlike fusion or fission, which release only a tiny fraction. But even annihilating an entire asteroid's worth of antimatter and matter together would barely move a small spacecraft a fraction of the way to light speed. Now, think about what infinite energy really means. Energy is the capacity to do work, to cause change. Infinite energy would mean an endless supply of power with no upper bound, something that violates every principle of physics we know. Conservation of energy, one of the most deeply rooted laws in science, simply forbids it. You can't get more out of the universe than what's already there. The cosmos itself has a finite energy content. Even if you harnessed every star, every planet, every atom, you still wouldn't come close. Light speed isn't just hard. It's literally off the scale of existence. There's also another way to think about this. As you accelerate and pump in more and more energy, the energy doesn't just make you faster, it begins to change your relationship with time and space. The faster you go, the slower time passes for you relative to an outside observer. As your energy grows, your perception of distance and duration shifts. From your own perspective, you may feel like you're still accelerating smoothly, but to an observer watching from afar, your progress slows asymptotically, never quite touching the barrier of light speed. This is nature's way of maintaining consistency. Every observer sees light traveling at the same speed, no matter how much energy you throw into the chase. In effect, the universe doesn't let you break the speed limit because doing so would require rewriting the geometry of space-time itself. The exponential climb of energy is not a technical flaw. It's the mathematical manifestation of reality's most fundamental structure. Einstein didn't just find a limit. He discovered a law that defines the interplay between motion, energy, and existence.
Even in speculative physics, when scientists dream about advanced civilizations harnessing stellar energy or building engines powered by black holes, the same problem arises. No matter how efficient or advanced the propulsion, you can't escape the infinite energy wall. Some theorists even argue that approaching light speed too closely would begin to distort space-time around the ship, creating gravitational effects that could tear it apart before it ever reached its goal. In that sense, the barrier isn't just energetic, it's existential. But this impossibility paradoxically gives us one of the most beautiful insights into how the universe works. It tells us that energy, space, and time are all part of the same cosmic equation. It tells us that every bit of acceleration comes at a cost, not just in fuel, but in the way the universe bends to accommodate your motion. And it tells us that perfection, in this case, the perfect speed of light, can exist only in the form of light itself. Still, the infinite energy wall is not the end of the story. It's the beginning of understanding why that wall exists. Because if infinite energy is impossible to obtain, then so is reaching light speed. This realization leads us naturally to the next question. Why can't we ever create or access infinite energy in the first place? Why does the universe impose such strict boundaries on what can be done? The answer lies in the very nature of energy itself, and in the delicate balance that keeps the cosmos from collapsing into chaos. The concept of infinite energy might sound abstract, but at its core, it's an impossibility that strikes at the very foundation of physics. The reason no object with mass can ever reach or exceed the speed of light is simple in statement, but profound in implication. Infinite energy doesn't exist, and the universe itself is built to make sure it never can. Every system in nature, whether it's a star, a galaxy, or a single particle, has finite energy. The total energy of the observable universe is vast beyond imagination, but it's still finite. That boundary, written into the laws of thermodynamics and relativity, is what keeps the cosmos coherent and prevents the impossible from happening.
To grasp why infinite energy is forbidden, we need to understand how energy works on both cosmic and local scales. Energy is the capacity to cause change. It can move objects, heat matter, bend space, and drive stars to shine, but it cannot be created from nothing or multiplied endlessly without consequence. This is the first law of thermodynamics, the law of energy conservation. Energy cannot be created or destroyed, only transformed. Even the most violent events in the universe, supernovae, black hole collisions, and gamma ray bursts, are simply energy changing form, not energy being born from nothing. The universe plays fair. No hidden account exists from which we can withdraw infinite energy. Now, when we say something would require infinite energy, what that really means is that the equations describing it diverge. They blow up into nonsensical values. It's not just that we can't find infinite energy, the concept itself breaks the mathematical framework of physics. If you try to accelerate a mass to light speed, Einstein's energy equation predicts the energy needed grows without bound. At 99% of light speed, you've already pumped in colossal amounts. At 99.9999%, the requirement becomes astronomical. Push closer still, and the curve doesn't plateau, it stretches into infinity. There's no final burst, no clever trick, no loophole that lets you cross that barrier. The energy wall doesn't move because it's not a wall of matter or force, it's a wall of reality. Think of the universe as a kind of cosmic economy. Energy is the currency that makes everything happen. Every process, every interaction, every motion must pay its price. The closer you get to light speed, the more expensive that motion becomes. Eventually, the cost isn't just high, it's infinite. And just as no bank account can pay an infinite bill, no engine, no star, no mechanism in existence can provide infinite energy. Even if you combined every galaxy's output, every atom's stored potential, and every flicker of dark energy across the cosmos, you would still fall infinitely short. Infinity isn't just large, it's unreachable by definition. This is why light itself stands apart. Photons, the particles of light, have no rest mass. They are born massless, exist massless, and travel at light speed naturally. Because they have no mass, they don't need energy to reach that speed. It's their intrinsic property. They don't accelerate to it, they exist at it. Anything with even a speck of mass, on the other hand, starts from zero and must be pushed, and that push requires energy. As speed rises, the required energy rises faster, forming an asymptote that the universe never allows you to cross. It's as if light occupies a highway reserved for the massless, and every object with mass is forever stuck in the slow lane, no matter how hard it presses the accelerator.
The impossibility of infinite energy isn't just a mechanical limitation. It's a principle that safeguards the universe's consistency. If infinite energy were somehow possible, it would break every law of thermodynamics. Temperatures would reach infinity, forces would become unbounded, matter and space-time themselves would tear apart. In such a reality, stable structures couldn't exist. No atoms, no stars, no galaxies, no you. The universe as we know it would dissolve into chaos. The cosmic speed limit and the impossibility of infinite energy are what allow a coherent, predictable universe to exist at all. Even our most extreme cosmic phenomena illustrate this boundary. Black holes, for instance, contain enormous amounts of energy concentrated into infinitesimal regions, but even they do not contain infinite energy. Their gravitational fields are intense enough to trap light, yet still finite in strength. The singularity inside a black hole, where equations predict infinite density, is not so much a real infinity as a signal that our current physics stops working there. It's nature's way of saying, this is beyond your model. The laws of relativity and quantum mechanics both fail under such conditions, and we need a deeper, unified theory to describe what truly happens. But even then, it's widely believed that no true infinity exists in nature, only limits that appear infinite when our understanding reaches its edge. If we imagine trying to accelerate a spaceship toward light speed, this impossibility becomes clear in more practical terms. Let's say you had a ship capable of converting matter directly into energy with perfect efficiency. Something no known technology can do, but let's assume it. To push that ship to 99% of light speed, you'd need a staggering amount of fuel, more than the ship's own mass converted into pure energy. To reach 99.9999%, you'd need to convert entire planets, maybe entire solar systems into energy. To get to 100%, you'd need to consume the entire universe, and it still wouldn't be enough. The exponential climb never ends. Infinite energy is not simply a high target, it's the unattainable asymptote of existence itself. This truth has humbling and liberating implications. On one hand, it limits us. We cannot simply brute force our way to the stars at light speed. On the other, it teaches us something profound about the universe. It's balanced. It's stable. It enforces its own order. Without those limits, there would be no structure, no flow of time, no causality. Every boundary we encounter, every physical constant that seems to frustrate our ambition, is also what makes life and order possible. So when we say that infinite energy doesn't exist, we're really acknowledging that the universe has boundaries built into its very design. These aren't walls meant to confine us. They're the scaffolding that holds reality together. And within those boundaries, we've still managed to achieve the extraordinary. Nuclear fusion, spaceflight, particle collisions at nearly the speed of light. Humanity may never reach the ultimate limit, but every step closer deepens our understanding of what that limit means. Still, the consequences of approaching light speed aren't only about energy. They also begin to bend the flow of time itself. As we near that boundary, the universe doesn't just demand infinite energy, it rewrites our experience of time. Clocks slow down, motion warps, and the fabric of reality flexes in ways that seem almost magical. The next revelation of relativity takes us even deeper into that mystery, the phenomenon known as time dilation, where speed doesn't just change how fast we move through space, it changes how fast we move through time. Time is one of those things we experience so intimately that it feels absolute. A steady rhythm that moves forward for everyone at the same pace. A second for you should be a second for me, and a minute should tick by identically no matter where we are or how fast we move. For most of human history, that assumption seemed unshakable. Yet Einstein's theory of relativity shattered it, revealing that time itself is elastic. It can stretch or compress depending on how fast you're moving or how strongly gravity tugs on you. This phenomenon, known as time dilation, is one of the strangest and most beautiful consequences of relativity. It tells us that time is not universal. It's personal. When an object begins to move at high speed, its flow of time slows relative to someone standing still. The faster it goes, the slower time runs for it. At ordinary speeds, this effect is minuscule, far too small to notice, but as you approach light speed, it becomes dramatic. If you could somehow travel at 99.99% of the speed of light, a single hour on your spaceship could correspond to years or even decades for someone back on Earth. To you, everything on the ship would seem perfectly normal. Your clock ticks, your heartbeat continues, you speak and move as usual. But if someone could watch you from Earth, they would see your actions in extreme slow motion. From their perspective, your time has stretched almost to a crawl. This isn't science fiction. It's real, measurable, and confirmed by countless experiments. Time dilation isn't just a theoretical idea scribbled in equations. It's a feature of the universe that we can test and use. One of the clearest proofs comes from studying muons, subatomic particles created when cosmic rays strike Earth's atmosphere. Muons have a very short lifespan. They decay in microseconds. At rest, they shouldn't survive long enough to reach the ground. Yet when they're created at high speeds, moving close to light speed, they're observed reaching the surface far more often than expected. The reason? Their internal clocks, their decay processes, are running slower due to time dilation. To the muons themselves, nothing feels different. But from our perspective, their time has stretched, allowing them to live longer.
Another famous example involves precise atomic clocks. Scientists have placed synchronized atomic clocks on high-speed jets and satellites while keeping identical ones on the ground. When the clocks reunite, they show slightly different times. The clocks that traveled faster through space or experienced weaker gravity ticked more slowly. The differences are tiny, mere billions of a second, but they are measurable with today's technology and perfectly match Einstein's predictions.
This isn't an abstract curiosity either. Modern systems rely on it. The Global Positioning System, GPS, for instance, must constantly correct for time dilation. The satellites orbiting Earth move fast enough and experience slightly weaker gravity than we do on the surface. So their onboard clocks tick faster than clocks on Earth. If we didn't account for those relativistic effects, GPS positions would drift by several kilometers each day. Relativity literally keeps your smartphone's navigation accurate. Now, imagine this effect on a grander human scale. Suppose you're an astronaut aboard a near-light-speed spacecraft traveling to a distant star 10 light-years away. To observers on Earth, your journey might take more than 10 years, even if you're moving close to light speed. But to you, inside the ship, time would pass much more slowly. Depending on your velocity, you might experience only a few years, or even months of travel. When you return to Earth, you'd find that decades or centuries had passed, while you aged only a small fraction of that time. This is not fantasy, it's a direct and inevitable consequence of time dilation. This idea is often called the twin paradox, one of the most famous thought experiments in relativity. Imagine two twins, one stays on Earth, and the other boards a spaceship and travels at near light speed, then returns. When they reunite, the traveling twin will be younger than the one who stayed behind. It's not because of any biological trick, it's because time itself passed differently for each of them. For the traveling twin, every clock, every heartbeat, every atomic vibration ran slower relative to Earth. The paradox dissolves once we understand that motion through space and motion through time are intertwined. Speeding through one reduces your movement through the other. From the traveler's perspective, nothing unusual happens. Time always feels normal to the person experiencing it because relativity doesn't change local experience. It changes how that experience compares to others moving differently. It's only when you bring the two reference frames together, when you compare clocks, or when the twins reunite, that the difference reveals itself. That's what makes time dilation so mind-bending. It's not an illusion or a trick of perspective. Time truly passes at different rates for different observers, depending on their motion through space-time. The deeper reason behind this is that the universe maintains a constant relationship between space and time through the speed of light. No matter how fast you move, the total combination of your motion through space and time remains fixed. If you move faster through space, you must move slower through time to compensate. Light itself, moving at the ultimate velocity, has no time at all. From a photon's point of view, it's emitted and absorbed instantly with no passage of time between. The rest of us, burdened with mass, live in a slower world where time flows at finite rates, and we can only approach, never reach, that timeless state of light. On a human scale, this concept invites both awe and melancholy. It suggests that if we could ever travel close to light speed, we could essentially journey into the future. For instance, traveling at 99.999% of light speed for a few years of personal time could correspond to centuries passing on Earth. When you return to Earth, you'd find your home world transformed, your friends and loved ones long gone, and the planet perhaps utterly changed. Time dilation offers us a kind of time travel, but one that only moves forward, never back. It's a one-way ticket through the future. Interestingly, time dilation doesn't only come from speed. It also arises from gravity, as shown by Einstein's later work on general relativity. The stronger the gravitational field you're in, the slower your clock runs compared to someone farther away. That's why time passes slightly slower for someone standing on Earth's surface than for someone in orbit. Near a black hole, this effect becomes extreme. A few minutes for someone hovering close to the event horizon could equal thousands of years to a distant observer. In both cases, high speed or strong gravity, time's flow is malleable, stretching and compressing under the influence of space-time itself. So when we talk about time dilation, we're really talking about the living, breathing flexibility of the universe. Space and time are not rigid, they yield and adapt to motion and energy. Every astronaut orbiting Earth, every particle racing through an accelerator, every photon streaming across the cosmos experiences its own tempo of existence. There is no single now that spans a universe. Each path through space-time has its own rhythm. And as we continue exploring what happens at near light speeds, we find that not only does time change, space itself begins to deform. Just as time slows down, distances in the direction of motion contract. This next phenomenon, known as length contraction, reveals another deep truth of relativity. The faster you move, the smaller the universe becomes in front of you. The rules of space, just like the rules of time, bend to ensure that nothing ever surpasses light speed.
Length contraction is one of those phenomena that sounds like pure science fiction until you realize it's not a product of imagination at all. It's a built-in feature of how the universe works. Just as time slows down when you move close to the speed of light, space itself bends to preserve the cosmic speed limit. According to Einstein's theory of special relativity, the faster an object moves, the more it appears to shorten along the direction of motion. It's not that the object physically compresses or feels squished to those inside it. Rather, from the perspective of an outside observer, distances along its path appear contracted. This effect, called length contraction, ensures that all observers, no matter how fast they're moving, will measure the same speed of light. No exceptions, no loopholes. To understand why this happens, imagine two observers watching the same event, one standing still and the other moving close to the speed of light. The moving observer experiences time more slowly because of time dilation, so to make the equations of the universe stay consistent, space must also adjust. If time slows down for the traveler, but the speed of light must remain the same, the only way to balance the scales is for distances in the traveler's direction of motion to shrink. This ensures that even though time ticks differently for each observer, the speed of light never changes. In other words, space and time trade flexibility. When one stretches, the other compresses, maintaining the unbreakable harmony of relativity. The contraction becomes noticeable only when speeds approach a significant fraction of light speed. At everyday velocities, even the speeds of jets or satellites, it's imperceptible. A spacecraft flying at, say, 30,000 kilometers per hour would shrink by less than a trillionth of a percent, a change so small that even the most precise instruments couldn't detect it. But as the velocity climbs toward relativistic levels, the effect grows astonishingly dramatic. At 90% of the speed of light, an object would appear about 44% shorter in the direction it's traveling. At 99.9%, it would look just 1/20th its normal length. Push that to 99.9999% of light speed, and an entire kilometer-long spaceship would seem barely a few meters long from the viewpoint of someone watching it zoom by. To the travelers on board, however, nothing feels out of the ordinary. Their ship feels exactly the same size. The cabin walls don't close in, their instruments don't distort, and they don't feel compressed. That's because, from their perspective, it's the rest of the universe that's distorted. The distances to stars ahead of them appear shorter. Relativity is symmetrical in that sense. Who's moving and who's still depends entirely on your frame of reference. If you're on the ship, you're at rest, and it's everything else that's moving. If you're on Earth, the ship is the one in motion. Both perspectives are valid, and both see the same underlying truth expressed differently through space-time. One of the easiest ways to visualize the length contraction is to imagine a light clock, a device where a beam of light bounces between two mirrors. When the clock is stationary, the light moves straight up and down. But if you start moving the clock forward, the light must travel diagonally to keep hitting the mirrors, creating a longer path. Because the speed of light is constant, it takes longer for the light to complete each round trip, which means the moving clock ticks more slowly. That's time dilation. To balance that, the distance between the mirrors must appear shorter to an outside observer, so that the speed of light remains constant for both the moving and stationary clocks. Time dilation and length contraction are therefore inseparable. They are two faces of the same cosmic coin, both ensuring the integrity of light speed in all frames of reference. This interplay between time and space reveals something profound. There's no such thing as absolute length any more than there's absolute time. The dimensions of space depend on how you move through it, and objects' true length doesn't exist universally. It depends on who's measuring and how fast they're traveling relative to it. This isn't just philosophical, it's measurable. Particle accelerators around the world, such as those at CERN, exploit length contraction every day.
When physicists accelerate protons to nearly the speed of light, the distances they travel and the fields they interact with must be calculated using relativistic formulas. At those speeds, a particle's internal electric field flattens, and the space it occupies becomes thinner along its path. These effects are critical for predicting collisions and ensuring the machinery operates correctly. Another striking example comes from cosmic rays, high-energy particles that constantly bombard Earth's atmosphere. When they strike, they produce showers of secondary particles, many of which decay too quickly to reach the surface if classical physics applied. But because they're moving near light speed, time dilation slows their internal clocks, and length contraction shortens the distance they need to travel. From their perspective, the atmosphere seems thinner. From ours, they last longer. The combination allows these fleeting particles to survive long enough for scientists to detect them, a real-world testament to how space and time distort in motion. If we ever built a spacecraft capable of reaching such extreme velocities, the same principles would apply. From the viewpoint of someone watching from Earth, the ship would appear flattened along its direction of travel, a streak of light, rather than a solid object. The closer it approached light speed, the more extreme the distortion would become, until it seemed almost two-dimensional. Inside the ship, though, astronauts wouldn't notice a thing. The journey would seem normal. They'd simply reach distant destinations much sooner than anyone on Earth would expect, because in their frame of reference, the distance itself has contracted. A star 10 light-years away might seem only a few light months distant. That's how relativity keeps the universe consistent, by letting travelers trade time for space and space for time.
The poetic beauty of length contraction lies in what it implies about reality. It tells us that the universe doesn't have a single objective shape that everyone agrees on. What's long for one observer might be short for another. Space isn't a fixed stage where events play out. It's woven together with time into a dynamic fabric that reshapes itself depending on motion. Every traveler, every photon, every atom moves along its own unique curve through space-time, carrying its own version of length and duration. And just as length contraction reshapes our understanding of space, there's another phenomenon that helps us understand why light alone can travel at the ultimate speed. Unlike any object we can build, light's particles, photons, don't experience time or distance the way we do at all. For them, the concepts of slower or shorter simply don't exist. To truly see why the speed of light is special, we need to understand what makes these massless travelers so fundamentally different from everything else in the cosmos. Light is extraordinary, not just because it moves fast, but because it occupies a fundamentally different category of existence. Its speed is the universal constant, the cosmic speed limit that nothing with mass can touch. The reason photons, the particles of light, can travel at this limit is deceptively simple. They have no rest mass. Unlike electrons, protons, spaceships, or planets, photons exist without the inertia that binds mass to the rules of acceleration. They do not need to be pushed, fueled, or accelerated. They simply move at light speed by their very nature. This absence of mass allows them to glide across the universe unimpeded, unaffected by the infinite energy barrier that holds back all massive objects. To understand why mass is the crucial factor, consider what happens when you try to accelerate anything with mass. As we discussed earlier, adding energy increases a massive object's velocity only to a point because relativistic mass rises and the required energy grows toward infinity. Photons, having zero rest mass, are exempt from this restriction. They don't push themselves to light speed, they are born moving at it. From the instant of their creation, whether emitted by a star, a laser, or a glowing filament, photons are already racing at 299,792 kilometers per second. They are exempt from the laws that limit massive objects. They are nature's ultimate travelers, forever untouchable by the constraints that bind us. It's important to note that photons aren't simply objects traveling fast in space. They are excitations of the electromagnetic field. They carry energy and momentum, yet without mass. This is why they can bend around gravitational fields, a phenomenon observed as gravitational lensing,
and yet still move at light speed. Even in the presence of extreme gravity, like near a black hole, photons always move locally at c. They are fully relativistic entities, not just ultra-light objects. Everything we build or experience, from cars to spacecraft, is made of matter, and that matter is governed by inertia, mass, and the relativistic restrictions that prevent light speed travel. Photons exist outside this limitation entirely. From a practical perspective, this is why photons are so important for exploring the universe. They are our messengers across time and space, carrying information from the furthest corners of the cosmos to our eyes and instruments. The light from distant stars and galaxies reaches us after traveling millions or billions of years, and because photons move at light speed, we see these celestial bodies as they were eons ago. In contrast, if we tried to send a massive probe to the same star, we would be trapped by energy limits and relativistic constraints, unable to reach even a fraction of that distance in a human lifetime. Photons bypass all these limitations simply because they are massless. Interestingly, photons also illustrate why light speed travel isn't just difficult, it's fundamentally different from anything we can build. No technology, no matter how advanced, can reduce a spacecraft's mass to zero. We cannot simply strip away the inertia that makes acceleration difficult. Even the smallest particle with rest mass, like an electron, would require infinite energy to reach light speed. We can accelerate particles very close to c, as in particle colliders, but we can never bridge that final gap. Light, however, faces no such gap. It doesn't approach light speed. It is light speed. It exists as the boundary itself. The behavior of photons also emphasizes the unique relationship between mass, energy, and spacetime. While photons have no rest mass, they do carry energy and momentum, meaning they can exert pressure, transfer force, and interact with matter. This is the principle behind solar sails, which propose using light itself to propel spacecraft across space. While we cannot make our ships massless, we can harness the energy and momentum of massless particles to push massive objects a little faster, although always far below the speed of light. Photons provide both an inspiration and a reminder. The universe allows speed and information, but only in certain forms, and mass is the key that determines the rules. Another fascinating aspect of photons is how they perceive time and space. Because they travel at c, they do not experience time or distance in the way we do. From the moment a photon is emitted to the moment it is absorbed, no time passes for it, and the distance it travels is effectively zero from its own perspective. This is why, in a sense, photons are timeless travelers. They experience the universe instantaneously, yet they carry information across incomprehensible expanses. It's a striking contrast to anything with mass, which experiences every fraction of distance and time and cannot escape the slow, inexorable march toward infinity as it accelerates. This distinction between massless and massive entities is central to understanding why faster-than-light travel is so profoundly challenging. We can study light, manipulate it, use it to communicate and explore, but we cannot become light. We are bound by mass, by inertia, by the relativistic laws that govern energy and acceleration. Photons demonstrate that light speed travel is possible in principle only for those entities that are inherently exempt from mass. For humans, spacecraft, or even the tiniest particles with rest mass, the speed limit remains unbroken, an absolute boundary set by the structure of the cosmos. From a philosophical perspective, photons are the universe's ultimate speedsters, the exception that defines the rule. They reveal the possibilities allowed by the laws of physics while simultaneously showing the limits imposed on everything made of matter. The very existence of massless particles sets the cosmic pace, demonstrating both what is possible and what is forever beyond our reach.
And yet, even as we confront the impossibility of matching light speed, practical problems remain for anything moving very fast. The faster you go, the more extreme other effects become. Beyond energy limits and the distinction between massless and massive entities, accelerating a spacecraft to relativistic speeds introduces profound engineering challenges. forces and pressures that are manageable at low speed become deadly at high speed, threatening the integrity of both ship and crew. The universe allows light to travel unimpeded, but for us, the journey is another story entirely. This brings us naturally to one of the next obstacles in the pursuit of relativistic travel, the problem of acceleration itself. Pushing a massive spacecraft to ever higher speeds may be mathematically conceivable up to some fraction of light speed, but doing so safely without crushing humans inside presents a challenge that is just as fundamental as the energy limits we've already explored. When we consider the idea of sending humans to distant stars at a significant fraction of light speed, one of the first physical challenges that comes to mind is acceleration itself. We often imagine a spaceship smoothly taking off, gaining speed like a car or a plane, and eventually reaching the vast velocities that bring the stars within reach. But unlike an automobile, which operates in a medium that cushions some of its motion, a spaceship carries its crew in open, unforgiving space, and the laws of physics don't bend for comfort. Accelerating a massive object gradually enough to approach relativistic speeds without crushing its occupants under extreme g-forces is one of the most daunting engineering problems we face. G-force, or gravitational force experienced during acceleration, is a measure of how much your body resists being pushed or pulled. On Earth, we're used to 1G, the force of gravity pressing us into the ground. Fighter pilots who routinely experience 5 to 9 Gs during maneuvers must use special suits and breathing techniques to avoid blacking out as blood is forced away from the brain. For space travel, even moderate acceleration over extended periods can be lethal if not carefully controlled. The human body is remarkably fragile compared to the energies involved in near light speed travel. If a spacecraft attempted to accelerate to a significant fraction of the speed of light over a short time, the forces would easily crush bones, collapse organs, and render the crew unconscious or worse. To avoid this, any interstellar ship would need to accelerate extremely gradually, sustaining only a tiny fraction of a G over years or decades. If the ship could maintain a constant acceleration equal to 1 Earth G, about 9.8 meters per second squared, the crew could experience a natural feeling of gravity, a significant advantage for long-term health in microgravity. This is often called a 1G Starship concept. At this rate, the spaceship could theoretically reach a substantial fraction of light speed after several years of continuous acceleration. But here lies the catch. Sustaining propulsion at this level for decades or centuries requires energy on an astronomical scale, far beyond anything humanity can currently produce or store. The challenges are compounded by the sheer distance and duration involved. Unlike short launches from Earth, interstellar travel would require acceleration for years, a constant management of fuel, temperature, and mechanical stresses on both the vessel and its systems. Every engine, every structure, every pipe and panel would be under continual strain. Even the most resilient materials could fatigue, warp, or fail under prolonged stress. Microscopic imperfections could amplify into catastrophic failures over decades of relativistic acceleration. Space travel at near light speed is not just a problem of energy, it's a problem of sustained structural integrity and crew survivability. Moreover, acceleration in space isn't just a matter of pushing forward. Unlike driving on Earth, where the friction between tires and road allows forces to be transferred safely, a spacecraft in a vacuum cannot rely on external support. The forces of acceleration act directly on the ship's structure and the crew. Even modest accelerations, if applied incorrectly, could tear parts of the ship apart or stress life support systems beyond tolerance. The longer the acceleration period, the more opportunities there are for small errors or mechanical fatigue to become mission-critical failures. Designing a ship that can withstand this while keeping humans safe is an engineering nightmare. There's also a subtle but important relativistic factor to consider. As the ship approaches a significant fraction of light speed, relativistic effects amplify the challenges of acceleration. For example, as relativistic mass increases with velocity, more force is required to maintain the same acceleration. What starts as a gentle 1G push at low speed demands ever more energy to continue as the craft nears light speed. While a photon doesn't need to be pushed at all, every gram of spacecraft mass resists acceleration more and more strongly,
compounding the energy problem we discussed earlier. The faster you go, the more your ship behaves as if it is heavier, meaning that keeping your crew safe with gentle g-forces becomes exponentially harder.
Even with perfectly distributed acceleration, shielding becomes a major concern. At relativistic speeds, the smallest particles in space, dust, micrometeoroids, or stray atoms, turn into lethal projectiles. Accelerating without proper shielding would be pointless because collisions would become catastrophic, a problem we'll examine in detail later. But proper shielding adds mass, and added mass makes acceleration more difficult, creating a vicious cycle. The heavier the ship, the more energy needed. The slower the safe acceleration must be, and the longer the journey takes. Current spacecraft designs, including proposals for interstellar travel like Breakthrough Starshot, attempt to mitigate some of these issues by eliminating onboard humans entirely. Tiny, unmanned probes can accelerate at thousands of Gs because there's no crew to crush. Light sails, propelled by powerful lasers, could theoretically reach significant fractions of light speed in a matter of minutes or hours. But for humans, the picture is entirely different. Even tiny fractions of these accelerations could be fatal. Until we find new ways to bend the rules of physics or fundamentally alter human tolerance, interstellar travel with passengers will require decades of slow, gentle acceleration, a painstakingly slow race against both distance and the unyielding limitations of our own biology. Additionally, acceleration challenges intersect with other constraints like energy supply and propulsion. A ship cannot accelerate without a source of energy, and generating continuous thrust for years would require not just massive fuel reserves, but also heat management systems, propulsion reliability, and radiation shielding. Every aspect of life aboard a near-light-speed vessel depends on maintaining acceleration within human-tolerable limits, or else the journey itself becomes impossible. Even the seemingly trivial issue of maintaining orientation or trajectory becomes non-trivial when forces accumulate over decades. The engineering requirements for constant human-safe acceleration may be the single most difficult hurdle in planning realistic interstellar voyages. Ultimately, the problem of acceleration illustrates the tension between physics and ambition. We understand the equations, the relativistic effects, and the energy requirements, but human biology is not designed for decades-long exposure to even mild g-forces combined with extreme radiation and isolation. Unlike photons, which move naturally at light speed, humans must be carefully coaxed through relativistic velocities, inch by inch, lest the voyage itself become lethal. It is a reminder that space travel is not just a technical challenge, but a fundamentally biological one. This consideration naturally leads to another major limitation: fuel and engineering constraints. Even if we could manage gentle acceleration for decades, the energy required to sustain propulsion, the structural demands of a spacecraft, and the need to shield both the crew and the vessel from space hazards combine to make near-light-speed travel far more complicated than just going fast. The acceleration problem is inseparable from these engineering realities, which together define the limits of what humanity could achieve. Even if we could solve the problem of acceleration, the question of fuel and engineering presents an obstacle of equal or greater magnitude. The physics of near-light-speed travel doesn't merely strain human endurance, it stretches our technological imagination to its breaking point. To accelerate a massive spacecraft to even a modest fraction of the speed of light requires a propulsion system that is orders of magnitude beyond anything we've ever built. Current chemical rockets, nuclear engines, and even speculative fusion drives are utterly inadequate when confronted with the vast energy scales demanded by relativistic speeds. The challenge isn't just about making a powerful engine, it's about sustaining thrust long enough to move enormous masses without violating the cosmic speed limit, all while surviving the unforgiving environment of space. To put this in perspective, consider our most powerful rockets, such as the Saturn V used for the Apollo missions.
That rocket could launch a payload of about 45 tons into low Earth orbit, but even at maximum thrust, it could barely achieve 0.00015% of the speed of light. Extending that to interstellar distances, we quickly see the enormity of the problem. If we wanted to reach even 10% of light speed with a spacecraft capable of carrying humans and supplies, the amount of fuel required would vastly exceed the mass of the entire planet. Chemical propulsion simply cannot store or release the necessary energy efficiently enough. The energy density of chemical fuels is far too low to make relativistic travel feasible. Nuclear propulsion improves the situation slightly. Fission and fusion reactions release orders of magnitude more energy per kilogram of fuel than chemical reactions. Concepts like nuclear thermal rockets or nuclear pulse propulsion, such as the famous Project Orion, envisioned detonating nuclear bombs behind a spacecraft to generate thrust. In theory, these designs could accelerate a craft to a few percent of light speed. But even then, the engineering hurdles are extreme. A human-rated spacecraft would require enormous shielding from radiation, thousands of nuclear devices, and extremely robust structural materials to survive repeated explosions. Pushing beyond a few percent of light speed quickly escalates fuel requirements to unrealistic levels. The fuel mass fraction problem, the need for more fuel than the total mass of the ship, becomes insurmountable. Fusion propulsion offers slightly better prospects. By fusing isotopes of hydrogen, such as deuterium and tritium, fusion rockets could produce vast amounts of energy relative to their mass. Designs like the Daedalus project, conceived in the 1970s, envisioned an unmanned probe accelerated to about 12% of light speed using fusion. While theoretically feasible on paper, this required thousands of tons of fuel and highly precise control over nuclear reactions at enormous scales. Sustaining such reactions for decades without failure is far beyond current engineering capabilities. And for a manned ship, the demands become even greater. Life support, shielding, structural integrity, and acceleration limits compound the difficulty.
Even more speculative concepts, such as antimatter propulsion, promise even higher energy densities. Matter-antimatter annihilation releases 100% of the mass as energy, orders of magnitude greater than nuclear fusion. If we could produce, store, and control antimatter safely, it might, in theory, accelerate a spacecraft to a significant fraction of light speed. Yet the production of antimatter is extraordinarily limited and inefficient. Today, particle accelerators create only nanograms of antimatter per year, at astronomical costs. Containing antimatter is equally challenging. Any contact with ordinary matter results in catastrophic explosions. While antimatter represents the theoretical upper bound for propulsion energy density, practical engineering makes it essentially unattainable with current or near-future technology. Another major problem is propellant mass ratio. To accelerate a spacecraft, you must eject mass in the opposite direction, the rocket principle. As the desired velocity approaches light speed, the ratio of fuel mass to payload mass grows exponentially. For example, achieving just 10% of light speed with conventional propulsion would require carrying hundreds of times the ship's payload mass in fuel. As velocity increases, this ratio becomes absurd. The energy required grows faster than any propulsion system can handle, creating a paradox. The more fuel you carry to go faster, the more massive the ship becomes, which in turn demands even more fuel to accelerate further. The cycle quickly becomes unsolvable. Beyond fuel, the engineering challenges are staggering. Sustaining a ship for decades or centuries in space requires materials that can withstand micrometeoroid impacts, radiation, and temperature extremes, all while maintaining structural integrity under constant low G-force acceleration. Life support systems must operate flawlessly for decades without maintenance. Energy storage and distribution systems must provide continuous power for propulsion, shields, and onboard systems. The cumulative mass of all these systems adds to the already enormous energy demands, making near-light-speed travel a technological impossibility for anything larger than a tiny probe. Even hypothetical propulsion technologies, such as light sails, which rely on photon pressure from lasers or the sun, illustrate these limitations. Light sails can accelerate very small spacecraft at extraordinary rates because they have minimal mass. Breakthrough Starshot, for instance, envisions sending gram-scale probes to Alpha Centauri at up to 20% of light speed using powerful ground-based lasers. While feasible for microscopic probes, scaling this to manned spacecraft introduces insurmountable problems. A human-carrying ship would be millions of times more massive, requiring an equally larger laser array and infrastructure that is orders of magnitude beyond what humanity could currently construct. All these factors demonstrate a fundamental truth. The faster we want to go, the more extreme the demands on energy, fuel efficiency, and engineering. Our current technology is simply incapable of producing the thrust, energy density, and structural resilience necessary to achieve even a small fraction of light speed for anything remotely human-rated. Unlike light, which has no mass and requires no fuel to move at sea, anything we build is bound by inertia, energy limits, and structural constraints. In essence, the fuel and engineering limitations form a second wall of impossibility, reinforcing the energy wall we explored earlier. Even if we could safely accelerate humans without crushing them, we could not supply the energy or propulsion necessary to sustain acceleration to relativistic speeds. These constraints highlight a critical point. Near light-speed travel is not merely a question of ambition or technology. It is a fundamental boundary imposed by physics and engineering realities. Until new breakthroughs occur in propulsion, energy generation, or material science, the dream of sending massive manned spacecraft to the stars at relativistic speeds remains firmly in the realm of theory. These challenges also hint at why many proposals for interstellar exploration focus on unmanned probes, light sails, or other alternatives that bypass the problems of mass, fuel, and human survival. If humans are ever to reach other star systems within a human lifetime, we may need to dramatically rethink not just propulsion, but the scale and nature of the ships themselves. And even then, other hazards await, such as the dangers posed by interstellar dust and collisions, which become exponentially more severe at near-light speeds. The universe is generous in its possibilities, but brutally restrictive in its rules. Traveling at near light speed is not just a matter of overcoming energy, propulsion, and acceleration challenges. It also means confronting the hostile environment of interstellar space itself. Space is often imagined as an empty void, a vast nothingness between stars, where a ship could sail unimpeded. In reality, even the most sparsely populated regions of space are filled with microscopic particles, tiny grains of dust, frozen molecules, and cosmic debris. At everyday velocities, these particles are mostly harmless. A speck of dust might sting if it hits your skin, but it certainly won't destroy a spacecraft. At relativistic velocities, however, the story changes dramatically. Those same grains of dust become lethal projectiles, capable of destroying entire ships. To understand the danger, consider the physics. Kinetic energy increases with the square of velocity, and as we approach light speed, relativistic effects amplify this energy even further. A grain of dust only a few micrometers across might weigh less than a billionth of a kilogram. At conventional speeds, it has negligible energy, but at 90% of light speed, the energy it carries is comparable to that of a hand grenade. Tiny particles accelerate in destructive potential by orders of magnitude as speed increases. Even a single collision could puncture the hull, destroy critical systems, or vaporize part of the spacecraft. At 99.9% of light speed, a particle the size of a grain of sand could release energy comparable to a small nuclear explosion upon impact. This isn't a theoretical concern. It's a fundamental consequence of relativistic motion.
Every particle in space is effectively a tiny bomb when approached at near-light velocities. The density of interstellar dust may seem negligible on a cosmic scale, roughly 1 particle per cubic centimeter in some regions. But over immense distances between stars, a ship would encounter countless particles. Traveling light years at relativistic speeds turns the sparse interstellar medium into a continuous hazard zone, where collisions are not a matter of if, but when. Even the tiniest mistakes in shielding or navigation could have catastrophic consequences.
Shielding against this threat is a monumental engineering problem. A thick, reinforced hull could protect against some collisions, but it also adds mass, and as mass increases, the energy and fuel required for acceleration rise sharply. The very act of protecting the spacecraft makes near-light-speed travel more difficult, feeding back into the same energy and propulsion constraints we've already discussed. Some theoretical designs propose using magnetic or plasma fields to deflect charged particles, but many interstellar grains are neutral and would pass through such defenses. There is currently no known technology that can fully eliminate the risk without imposing prohibitive mass and energy penalties. Even more alarming is that impacts are not limited to individual particles. Micrometeoroids, small rocks or chunks of ice, are less common, but their energy at relativistic speeds would be devastating. A collision with an object just a few centimeters across could release energy equivalent to thousands of tons of TNT. At light-speed velocities, spacecraft essentially become high-energy targets moving through a cosmic shooting gallery. There is no slow-down option for massless protection. Even fractional reductions in speed don't significantly reduce the destructive potential. The faster you go, the less room for error exists. Relativistic collisions also create secondary hazards. When a particle strikes the hull at near-light speed, it generates a cloud of plasma and radiation. These secondary effects can propagate through the ship, damaging electronics, disrupting navigation systems, and endangering crew health. Cosmic rays and high-energy particles already pose challenges for current spacecraft, but at near-light speeds, even interstellar dust becomes a high-energy radiation source, turning the environment into a relentless gauntlet. Protecting humans from these effects would require shielding orders of magnitude beyond anything we currently use for space missions. The problem also scales with distance. A journey to the nearest star system, Proxima Centauri, is just over 4 light-years away. While that may seem short in cosmic terms, traveling at relativistic speeds means encountering countless particles along the path. Even if collisions are rare, each one carries exponentially more energy than at conventional speeds, making survival dependent on near-perfect shielding and navigation. The longer the trip, the higher the probability of catastrophic failure from a single tiny grain. This danger fundamentally limits how fast we can safely travel through interstellar space. Even if we had enough energy and acceleration capacity to approach light speed, the interstellar medium itself becomes an adversary that cannot be ignored. Space is not empty, it's a minefield where relativistic effects turn the smallest obstacles into existential threats. Any design for a near-light speed spacecraft must contend with this reality, balancing acceleration, shielding, mass, and fuel in a delicate, almost impossible trade-off. Beyond the obvious threat to the spacecraft, interstellar dust collisions also highlight a subtle but important aspect of relativity. Kinetic energy scales dramatically at high velocities. The difference between ordinary impacts and relativistic impacts is not linear. It grows faster than intuition suggests. This means that hazards which seem trivial at low speeds suddenly dominate every design consideration at near-light speeds. Protecting a crewed ship becomes a problem of physics, not engineering imagination alone. Even hypothetical solutions like ablative shielding or electromagnetic deflection face limits. Ablative shields can absorb and dissipate energy from small particles, but erode over time, requiring resupply or self-repair, something impossible on multi-decade interstellar missions. Magnetic shields can deflect charged particles, but the neutral component of interstellar dust remains unaffected. Furthermore, the energy required to maintain such systems increases with the ship's velocity and mass, feeding back into the energy and propulsion barriers we've already explored. Ultimately, interstellar dust hazards underscore a stark truth. Near light speed travel is not just about engines and energy, but survival in a universe that becomes actively hostile at extreme velocities. Every tiny grain of matter, previously harmless, becomes a potential weapon, making the empty void of space one of the most dangerous environments imaginable. Humans, who have evolved to endure the gentle gravity and atmosphere of Earth, face an entirely different set of threats when trying to traverse the stars at relativistic speeds. The higher we try to push toward light speed, the more pronounced these hazards become, creating another immutable barrier to faster-than-light travel. This hazard also ties directly into another consequence of relativistic motion. The energy released in collisions becomes unimaginably high, transforming even microscopic particles into sources of enormous kinetic energy, effectively turning the cosmos into a minefield. This leads naturally to the next challenge. Relativistic energy collisions, or even grains of interstellar dust, can unleash forces equivalent to large explosions, emphasizing how lethal high-speed travel can be. As we push toward near-light speeds, the universe itself becomes a far more dangerous place, not because of some malevolent force, but because of the sheer physics of motion. Every tiny particle in space, a speck of dust, a stray atom, or a microscopic ice fragment, carries minuscule energy at normal speeds. At relativistic velocities, however, that energy skyrockets due to the effects of special relativity. The kinetic energy of a moving object isn't simply proportional to its mass and velocity squared anymore. It grows dramatically as speeds approach the speed of light. This is why even a single grain of dust can become an extraordinarily powerful weapon when encountered by a spacecraft traveling near sea. To put numbers on it, imagine a dust particle only a millimeter across, something that would be harmless at everyday velocities. At 0.9 c, 90% of light speed, this tiny particle would strike with energy equivalent to a large conventional bomb, capable of vaporizing portions of a spacecraft hull or crippling critical systems. At 0.99 c, the same particle could release energy comparable to a small nuclear detonation. The energy scales exponentially with speed, meaning that as you approach 99.999% of light speed, even micron-sized dust particles carry enough energy to obliterate anything in their path. For perspective, a grain of sand at near light speed would release energy measured in tons of TNT, a force utterly incompatible for survival for humans or structural integrity for a spacecraft. This phenomenon isn't just theoretical. Particle accelerators provide a microcosm of this effect. Protons and other subatomic particles are routinely accelerated close to light speed in colliders like the Large Hadron Collider. At these speeds, even individual protons carry enormous kinetic energy, comparable to that of a fast-moving mosquito, but concentrated in a single subatomic particle. When these particles collide with a target, they release energy sufficient to produce showers of secondary particles, demonstrating how destructive high-speed impacts can be. The LHC provides a scaled-down, controlled illustration of what a tiny particle could do to a macroscopic object if it were moving at the same relative velocity.
The danger isn't limited to small grains either. Larger micrometeoroids, or frozen fragments, which are relatively rare in the interstellar medium, would pose catastrophic threats at relativistic speeds. A fragment a few centimeters in diameter, traveling at 0.99 c, could release energy equivalent to thousands of nuclear warheads detonating simultaneously. The universe essentially turns into a high-speed firing range, where the odds of encountering a lethal particle increase with distance and speed. Shielding against these impacts is a monumental engineering challenge, because traditional materials would be insufficient to absorb or deflect the immense energies involved without adding prohibitive mass. One proposed method for mitigating these risks is forward ablative shielding, where the outer layers of a spacecraft are designed to vaporize and absorb incoming impacts. While this could protect against smaller particles, it comes with significant trade-offs. Each vaporized layer erodes the shield, requiring immense reserves of material to sustain a long interstellar journey. Additionally, at extremely high speeds, the impact energy might be so high that even the ablation cannot prevent penetration or secondary damage. The smallest miscalculations could mean catastrophic failure. Magnetic or plasma shields have also been proposed to deflect charged particles, but the majority of interstellar dust is neutral, making these approaches only partially effective. Beyond structural damage, relativistic collisions create secondary hazards that compound the danger.
When a particle strikes at near light speed, the impact releases energy not just in the form of heat or kinetic force, but also as high-energy radiation. X-rays, gamma rays, and secondary particle showers emanate from the impact point, potentially compromising electronics, navigation systems, and life support. Human crews exposed to these effects would be at extreme risk without massive weighty shielding, again, introducing the mass versus propulsion dilemma. At high velocities, every collision becomes a multifaceted hazard, threatening both the ship's integrity and the crew's survival simultaneously. These relativistic collisions illustrate another profound aspect of approaching light speed. The universe does not scale linearly with our intuition. Small objects that are harmless at normal velocities become weapons of unimaginable destructive potential. A spacefaring vessel would essentially be moving through a minefield of particles, where even the tiniest speck could end the mission. The higher the speed, the more lethal the environment becomes, not because space has changed, but because the physics of motion magnifies the energy carried by every encountered particle. This catastrophic risk is a crucial reason why the design of near-light-speed spacecraft is so profoundly constrained. Even with unlimited fuel, perfect engines, and low g-force acceleration, the relativistic environment itself imposes an almost insurmountable hazard. It is not enough to accelerate safely. One must also survive the journey, protected from the cumulative energy of countless high-speed collisions. Unlike chemical or nuclear explosions, these impacts are stochastic, unpredictable in exact location and timing, making risk mitigation even more complex. The magnitude of this challenge also demonstrates why small, lightweight, unmanned probes are the primary candidates for near-light-speed exploration. Breakthrough Starshot, for example, envisions gram-scale spacecraft that can be accelerated to a significant fraction of c. At such tiny scales, the damage from particle collisions is less catastrophic, and any loss of individual probes is relatively inexpensive compared to sending humans. But scaling these concepts up to a full-sized, crewed starship would multiply the energy of every collision by the mass and cross-sectional area of the ship, creating an environment where even survival, in theory, becomes almost impossible. Relativistic energy collisions are more than just a theoretical concern. They're a practical demonstration of why near-light-speed travel is extraordinarily dangerous for massive objects. They tie together all the other relativistic limitations we've discussed: energy requirements, acceleration limits, shielding challenges, and amplify them to the point where the physics of space itself becomes a deadly barrier. In essence, the universe ensures that approaching light speed with anything that has mass is not merely difficult. It is an environment where the smallest mistakes or unavoidable obstacles carry lethal consequences. This reality has profound implications for interstellar travel. It explains why concepts like warp drives, wormholes, or other exotic faster-than-light mechanisms are so alluring in science fiction. Only by bypassing normal space and relativistic physics could humanity hope to evade the hazards of relativistic collisions. But even in theory, these approaches require exotic physics that we currently don't understand or engineering challenges that are currently insurmountable. Before we can think about bending space or warping reality, we must first confront the brutal fact that traveling through space at near light speed transforms even the most innocuous cosmic dust into catastrophic threats. The problem of relativistic collisions naturally leads into discussions of theoretical concepts like warp drives, where the idea is to move space-time itself rather than the ship, potentially bypassing these collisions altogether. But even as these ideas face staggering theoretical and engineering hurdles, reminding us that the speed of light is not just a number, it's a boundary that shapes every facet of interstellar exploration. For centuries, the concept of traveling faster than light has captivated human imagination. Science fiction is full of warp drives, hyperspace jumps, and wormholes. Fantastical ideas that allow spacecraft to traverse the galaxy in hours or days, defying the immense distances that would otherwise take decades, centuries, or even millennia to cross. These ideas are alluring because they seem to sidestep all the physical obstacles we've discussed. The energy barriers, the relativistic mass increase, the lethal interstellar dust, and the impossibility of carrying in a fuel for near light speed travel. Yet despite being tantalizing, these concepts remain almost entirely theoretical, constrained by physics we don't yet understand and engineering challenges that are currently insurmountable. Warp drives are one of the most famous theoretical constructs. The basic idea is deceptively simple in concept. Instead of moving a spaceship through space at light speed, you manipulate space-time itself. By contracting space in front of the ship and expanding it behind, the ship could be effectively carried along by a wave of distorted space. The craft itself might remain nearly stationary within this bubble, avoiding many of the problems that come with traditional acceleration. In principle, this would allow the ship to traverse vast distances faster than light could in normal space, because it's not actually moving through space in the conventional sense. It's moving space itself. In theory, such a method could evade relativistic energy limits, G-force issues, and the lethal interstellar dust.
The most well-known mathematical model for this is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. His equations showed that general relativity allows, under very specific conditions, a space-time bubble in which faster-than-light travel is mathematically possible. The ship would sit in a locally flat region of space, protected from the effects of relativistic travel, while the warp bubble moves the ship along at superluminal speeds relative to the outside universe. It's a breathtaking idea because it promises to bypass almost all of the limitations that make traditional relativistic travel so deadly and inefficient. However, there are enormous caveats. First and foremost, creating a warp bubble requires exotic matter with negative energy density, something that has never been produced in quantities anywhere near what would be necessary. Our current understanding of physics allows for small amounts of negative energy in certain quantum phenomena, like the Casimir effect, but scaling that to move a spacecraft spanning tens or hundreds of meters is beyond anything feasible with present technology. Theoretical calculations suggest that the energy required might exceed the mass energy of entire stars, depending on the size and speed of the bubble. Even if we could somehow reduce this requirement, engineering a stable bubble without collapsing it or generating destructive radiation is an entirely unknown challenge. Wormholes present a related idea, and one that is equally fascinating yet perilous. A wormhole is a hypothetical shortcut through space-time, connecting two distant points via a tunnel-like structure. In principle, traveling through a wormhole could allow a spacecraft to instantaneously cover distances that would otherwise take thousands of years. Theoretical models in general relativity allow such structures to exist mathematically, but, as with warp drives, maintaining a stable wormhole would require exotic matter with negative energy to prevent it from collapsing. Furthermore, the tidal forces near a wormhole could be extreme, potentially stretching or compressing a spacecraft or even a human beyond survivable limits. Even putting aside energy and stability issues, creating or finding naturally occurring wormholes presents staggering practical problems. We have no evidence that traversable wormholes exist in our universe. If they do, they may be microscopic or extremely short-lived. Engineering a wormhole large enough for a spaceship, keeping it open for a practical time span, and stabilizing the environment inside would demand technologies and materials far beyond anything humanity has imagined. For now, wormholes are firmly in the realm of speculative physics, offering a conceptual glimpse at possibilities that may or may not exist in nature. These theoretical ideas illustrate a critical point. Faster-than-light travel, while mathematically imaginable in certain frameworks, remains astronomically distant from practical reality. Even if the underlying physics permits it, the technological hurdles are unlike anything humans have faced before. Producing sufficient exotic matter, controlling space-time distortions, shielding occupants from relativistic radiation generated at the edges of a warp bubble, and navigating the altered geometry of space-time, all of these are profound problems. Our current spacecraft designs, engines, and energy sources
cannot even remotely approach what would be required. Nevertheless, the appeal of warp drives and wormholes is more than just imaginative. They serve as a framework for understanding the limits imposed by relativity. They provide a lens through which scientists can explore the boundaries of physics, asking questions like, what conditions must exist to allow faster-than-light travel? Can negative energy be produced and harnessed safely? How does space-time behave under extreme manipulation? Even if warp drives remain science fiction, the study of such possibilities pushes the boundaries of theoretical physics and may lead to insights we cannot yet foresee. Other sci-fi-inspired ideas, such as hyperspace or subspace travel, typically bypass physics entirely, invoking dimensions outside of our observable universe. These are not constrained by relativity in their fictional narratives, but they underscore a key point. Any faster-than-light scheme in reality must contend with the very real physics of mass, energy, and spacetime. Without some method of circumventing these constraints, either through space-time manipulation or an as-yet undiscovered mechanism, humanity remains tethered to sub-light speed travel, no matter how advanced our technology becomes. It's worth noting that even proponents of warp drive concepts are cautious. While Alcubierre's model shows a loophole in general relativity, converting that mathematics into engineering reality is not just difficult, it may be fundamentally impossible. We do not yet know whether the universe allows the construction of macroscopic warp bubbles without violating other laws of physics, such as causality or conservation of energy. Even if small-scale experiments could simulate aspects of a warp field, scaling that up to a starship is so extreme that it is essentially beyond comprehension with current knowledge. Despite all these limitations, warp drives and wormholes continue to capture the imagination of both scientists and the public because they represent the tantalizing possibility of escaping relativity's rigid constraints. They offer a vision of travel that avoids the deadly hazards of interstellar dust, the infinite energy required for mass-based propulsion, and the limits imposed by time dilation and length contraction. In other words, they provide a theoretical way around the universe's strict rules. But even as we dream of warping spacetime or stepping through wormholes, we must remember that these remain speculative. They illuminate the challenges of interstellar travel more vividly than any spaceship diagram. They highlight the impossibility of conventional near-light-speed journeys, show how deeply the speed of light governs the universe, and underscore the gulf between imagination and achievable technology. Until we understand exotic matter, negative energy, and the full behavior of spacetime, faster-than-light travel will remain a concept best explored in equations and science fiction, rather than reality. This naturally brings us to the next logical question. If warp drives are theoretical, could there be a realistic implementation in physics? One of the most discussed concepts here is the Alcubierre drive, which formalizes the idea of bending spacetime instead of moving through it. Understanding its principles requires a closer look at the exotic matter problem and the mechanisms by which a warp bubble would theoretically operate.
The Alcubierre drive represents one of the most fascinating intersections of theoretical physics and science fiction, and it offers a glimpse of how humanity might, in principle, sidestep the harsh limitations of relativistic travel. Unlike conventional propulsion, which accelerates a spacecraft through space and contends with the relativistic increase in mass, the Alcubierre concept doesn't move the ship in the traditional sense at all. Instead, it proposes manipulating space-time itself, contracting it in front of the ship and expanding it behind. This creates a warp bubble in which the spacecraft sits in a locally flat region of space, essentially riding a wave of distorted space-time. From the ship's perspective, it experiences no motion, no extreme acceleration, no crushing g-forces, no relativistic mass increase. Yet, relative to an outside observer, it can traverse vast distances at effective speeds faster than light.
Mathematically, the idea arises directly from Einstein's general relativity equations. General relativity allows space-time to bend, stretch, and curve in response to energy and mass. Alcubierre's insight was to envision a configuration where space-time itself could be engineered into a specific shape, compressed ahead of the ship and expanded behind. The ship remains in a pocket of unaltered space-time, preserving the safety of the crew and avoiding the conventional constraints of acceleration or collision with interstellar particles. In theory, this allows instantaneous light travel across light years without ever violating local physical laws, because the ship is not moving faster than light within its own space-time bubble. It's space itself that is moving. Despite its elegance, the concept comes with a formidable and perhaps insurmountable requirement: exotic matter with negative energy density. In classical physics, energy is always positive. To warp spacetime in the way that Alcubierre drive demands, portions of the bubble would need negative energy to repel space in one direction and attract it in another. This negative energy essentially creates a push-pull effect on spacetime, allowing the bubble to expand and contract. While quantum mechanics does allow for small amounts of negative energy in certain contexts, such as the Casimir effect, where vacuum fluctuations between two plates produce a tiny negative energy density, these amounts are minuscule. Scaling that to a starship-sized bubble capable of traversing light years is far beyond anything we can currently produce or imagine producing. The energy requirements for a practical Alcubierre drive are staggering. Early calculations suggest that it would require energy equivalent to the mass energy of an entire planet, or even multiple stars, just to generate a warp bubble for a modestly sized spacecraft. More recent refinements have reduced the estimate somewhat, but the required energy remains astronomically beyond human capability. It's not merely a question of finding a bigger power plant. It's a fundamental issue of physics. The negative energy density necessary to stabilize the bubble simply doesn't exist in usable quantities. And even if we could produce it, confining and controlling it poses engineering problems we cannot currently solve. Another concern is stability and causality. A warp bubble is not a passive phenomenon. It exists in a delicate balance. Any fluctuations in energy density could collapse the bubble, creating catastrophic consequences for the ship and crew. Simulations suggest that the walls of a warp bubble could accumulate high-energy particles, which would be released violently when the bubble is stopped or disrupted. Navigating this safely would require precise control over an exotic, high-energy system on a scale that borders on the unimaginable. Furthermore, the theoretical Alcubierre drive could produce horizons within the bubble, regions from which information cannot escape. This raises questions about whether the ship could communicate with the outside world or even navigate safely without catastrophic surprises. In addition to energy and stability challenges, there are unresolved questions about the causal structure of spacetime. Faster-than-light travel, even in a warped space-time bubble, could potentially allow for closed time-like curves, essentially loops in time that might permit paradoxical events. Physicists are still debating whether these theoretical issues make faster-than-light travel fundamentally impossible, even if the energy and engineering challenges could be overcome. It's one thing to generate negative energy, it's another to do so in a way that doesn't violate fundamental laws of physics or risk creating dangerous temporal anomalies. Despite these formidable challenges, the Alcubierre drive remains an extraordinary thought experiment because it shows that general relativity does not explicitly forbid faster-than-light travel. It demonstrates a loophole of sorts. By manipulating the geometry of space-time itself, we might bypass the relativistic constraints that limit mass-bearing objects. Unlike conventional near-light-speed travel, where collisions, energy, and acceleration make interstellar voyages nearly impossible, the Alcubierre concept avoids these hazards, at least on paper. The drive sidesteps g-force problems, mitigates length contraction issues, and potentially avoids the destructive energy of interstellar dust by allowing space itself to carry the ship.
In a broader sense, the Alcubierre drive exemplifies the contrast between what physics permits in theory versus what engineering makes possible. Mathematics may allow a warp bubble, but creating it demands physics we don't understand and energy we cannot access. It illustrates a recurring theme in interstellar travel. The universe provides glimpses of faster-than-light possibilities, but our current technology, materials, and understanding of energy make them effectively unreachable. Just as photons can traverse space at light speed because they have no mass, the Alcubierre drive suggests a method to cheat the rules, but only through mechanisms that remain entirely speculative.
In conclusion, the Alcubierre drive remains both inspiring and sobering. It is inspiring because it reveals the remarkable flexibility of spacetime under Einstein's equations, suggesting that the universe may contain pathways for superluminal travel that humans have only begun to imagine. It is sobering because it highlights how far removed these ideas are from technological reality. Without exotic matter, negative energy, and precise spacetime control, the drive remains a theoretical construct. In essence, it is a beacon for what might be possible if we could manipulate the very fabric of the cosmos, a tantalizing vision that motivates research into exotic energy forms, quantum gravity, and advanced theoretical physics, even if we cannot hope to build one anytime soon. From this concept, we naturally confront the next layer of difficulty in faster-than-light or near-light-speed travel, the intersection of quantum mechanics and gravity. While the Alcubierre drive deals with space-time on a classical level, any realistic understanding or creation of such a system would require a unified theory of quantum gravity, something that remains one of the most profound, unsolved problems in physics. Even if we imagine a theoretical Alcubierre drive or other exotic space-time manipulation, there is a deeper, more fundamental obstacle lurking beneath the surface: our incomplete understanding of how quantum mechanics and general relativity interact. Faster-than-light travel, especially anything involving manipulation of space-time itself, requires a level of physics that we currently cannot access. While Einstein's theory of general relativity describes gravity and the curvature of space-time exceptionally well on large scales, and quantum mechanics explains the behavior of particles at the smallest scales with astonishing precision, combining these two frameworks into a single consistent theory remains one of the greatest unsolved problems in science. Without such a unifying theory, any discussion of practical warp drives, traversable wormholes, or controlled manipulation of spacetime remains speculative at best. The conflict arises because quantum mechanics and general relativity operate under fundamentally different principles. General relativity treats spacetime as a smooth, continuous fabric that can be warped and stretched by energy and mass. It is deterministic, meaning that if you know the state of a system at one point, you can, in principle, calculate its future evolution. Quantum mechanics, on the other hand, is probabilistic, operating on discrete packets of energy and particles that can exist in superpositions, entangled across vast distances, and inherently uncertain until measured. At extreme conditions, such as those that would exist near the edges of a warp bubble or at the Planck scale, the smooth spacetime of relativity clashes with the jittery probabilistic nature of quantum phenomena. The mathematics of one breaks down under the assumptions of the other. One major implication is that even if we could generate negative energy or exotic matter, we don't know how quantum effects would behave under such extreme spacetime distortions. Quantum fields in highly curved spacetime may exhibit strange behaviors, potentially destabilizing a warp bubble or creating unforeseen energetic consequences. For example, Hawking radiation near black holes demonstrates that quantum effects in strong gravitational fields produce particles from the vacuum itself. Could similar quantum phenomena occur at the walls of a warp bubble, releasing bursts of high-energy particles that might destroy the spacecraft or render the drive unusable? The truth is, we don't know because we lack a fully developed theory of quantum gravity that can describe such situations. Another critical issue is the nature of spacetime at the smallest scales.
Many quantum gravity theories suggest that space-time is not continuous, but granular, with discrete chunks at the Planck length, approximately 10 to the minus 35 meters. If this is true, the smooth space-time required to create a stable Alcubierre bubble may not exist in reality. Manipulating space at macroscopic scales while accounting for quantum granularity may introduce instabilities that make a warp bubble impossible to maintain. Essentially, the very fabric of the universe could resist the manipulations necessary for faster-than-light travel.
Even more conceptually troubling is the problem of causality. Faster-than-light travel inherently risks creating closed time-like curves, effectively allowing for time loops where cause and effect become ambiguous. Quantum mechanics has rules that preserve causality at small scales, while general relativity allows spacetime geometries that could violate it at large scales. Without a unified theory, we cannot predict whether these violations would occur, or whether they would render faster-than-light travel impossible due to fundamental paradoxes. Imagine creating a scenario in which your spacecraft arrives before it departs. The physics of such a situation are completely unknown and could be catastrophic if not inherently forbidden by some deeper principle. These challenges highlight why many scientists treat warp drives and similar concepts as purely theoretical exercises, rather than achievable engineering projects. While we can write equations suggesting that spacetime manipulation is mathematically allowed, the lack of a consistent framework that merges quantum mechanics with general relativity means we cannot reliably predict the outcomes of such manipulations. It is one thing to theorize about negative energy, spacetime contraction, or wormhole stabilization. It is an entirely different matter to implement them safely in the real universe, governed by unknown quantum gravitational effects. Practical consequences for faster-than-light travel are profound. For instance, even if exotic matter were somehow discovered or produced, we cannot currently model how it interacts with quantum vacuum fluctuations, virtual particles, or gravitational anomalies. Any attempt to create a warp bubble or stabilize a wormhole could trigger quantum instabilities, producing uncontrolled energy releases, intense radiation, or total collapse of the spacetime structure. The universe may have built-in mechanisms encoded in quantum gravity that prevent macroscopic faster-than-light travel, analogous to how relativity prevents massive objects from reaching light speed in normal space. Interestingly, research into quantum gravity, string theory, and loop quantum gravity often intersect with the conceptual foundations of warp drives. By examining the edges of what physics allows, scientists explore whether negative energy densities, exotic spacetime topologies, or microscale spacetime manipulations could exist at all. These studies, while far from practical application, may eventually illuminate whether faster-than-light travel is fundamentally prohibited or merely technologically inaccessible. For now, the consensus remains, without a unified theory of quantum gravity, we are fundamentally blind to the full consequences of trying to warp spacetime. This intersection of quantum mechanics and gravity also underscores why current experimental approaches focus on near light speed travel rather than true faster-than-light travel. Particle accelerators, like the Large Hadron Collider, can propel protons to 99.9999% of light speed, allowing us to explore relativistic effects in the lab. But even there, quantum and relativistic effects must be carefully accounted for to predict particle behavior. Scaling up from subatomic particles to macroscopic spacecraft introduces layers of complexity where quantum gravitational phenomena may dominate, creating obstacles that are currently entirely beyond our predictive capability. Ultimately, these quantum and gravity challenges form the deepest barrier to superluminal travel. Energy, acceleration, shielding, interstellar hazards, and relativistic effects are all significant, but quantum gravity presents a more fundamental limit. We simply do not yet understand how matter, energy, and spacetime behave at the scales and conditions necessary for faster-than-light travel. Until physics progresses to unify these domains, any discussion of warp drives, traversable wormholes, or Alcubierre-like spacetime engineering remains speculative. Tantalizing in theory, but completely ungrounded in experimental reality. Given these limitations, humanity's realistic ambitions are focused not on breaking the speed of light, but on achieving fractional light speed travel. Even reaching 10% or 20% of light speed could open the stars to exploration within lifetimes.
sidestepping the unsolved problems of quantum gravity and exotic energy while still pushing the boundaries of what is physically achievable. Projects like Breakthrough Starshot are designed around these principles, demonstrating that subrelativistic interstellar travel is challenging but feasible, unlike the speculative realm of warp drives. While theoretical discussions of warp drives and quantum gravity stretch the imagination, humanity's current approach to near-light-speed phenomena is grounded firmly in experimentation with particle accelerators. These colossal machines, like the Large Hadron Collider at CERN, allow physicists to accelerate subatomic particles, protons, electrons, and heavy ions, to incredibly close to the speed of light. These experiments provide a tangible demonstration of relativistic physics and serve as the closest practical realization of near-light-speed travel that we currently have, even if only for microscopic particles rather than macroscopic spacecraft. They also highlight the staggering limitations of our existing technology when it comes to scaling these phenomena up to objects with mass and volume.
At the LHC, protons are accelerated to more than 99.9999991% of light speed, carrying energies on the order of 7 tera-electron-volts, TeV, per particle. At these velocities, relativistic effects become extremely pronounced. The protons experience a significant increase in effective mass, which in turn requires exponentially more energy to accelerate even further. This is exactly the same physics that would apply to a spacecraft trying to approach light speed. As velocity rises, mass increases, energy requirements skyrocket, and achieving additional acceleration becomes exponentially more difficult. The particle collider is a vivid demonstration of how extreme the energy barrier becomes at velocities approaching c. One of the key lessons from these experiments is the sheer energy scale involved. Accelerating a proton to near light speed requires an enormous electromagnetic infrastructure, including kilometers of superconducting magnets to steer the particles along a precise circular path, ultra-high vacuum conditions to prevent collisions with residual gas molecules, and highly specialized radio frequency cavities to impart energy incrementally. All this infrastructure is devoted to particles with masses on the order of 10 to the minus 27 kilograms. Scaling this up to a spacecraft weighing thousands of tons illustrates the insurmountable energy problem. The infrastructure and energy requirements would increase by orders of magnitude beyond anything humanity can produce or sustain. The accelerators also demonstrate relativistic phenomena in a concrete way. Time dilation, length contraction, and relativistic mass increase are all measured directly in these experiments. For instance, unstable particles that would decay in microseconds at rest live significantly longer when traveling near light speed, confirming time dilation predictions. This provides not just experimental confirmation of Einstein's theories, but also a stark illustration of what would happen to a macroscopic ship as it approaches similar velocities. The same effects that allow protons to live longer at high speeds would, for humans, manifest as profound time dilation. Decades of travel for the crew could correspond to centuries passing in the rest of the universe. Colliders also make clear the engineering limits of containment at near-light speeds. Even at microscopic scales, steering particles requires extreme precision. Magnetic fields must be carefully tuned, and any tiny perturbation can cause the particles to collide with the accelerator walls, releasing enormous energy. A single errant particle carries kinetic energy far beyond that of macroscopic objects at conventional speeds, which is why accelerator walls must be designed to absorb and dissipate energy safely. Now, imagine scaling this up to macroscopic spacecraft. The precision required to avoid catastrophic collision with interstellar dust or to maintain course becomes almost unimaginably difficult. Near light speed travel magnifies even the smallest errors into potential disasters. Another insight from particle accelerators concerns energy loss mechanisms. Protons and electrons traveling near light speed emit radiation, synchrotron radiation, when their paths are bent by magnetic fields. This energy loss is proportional to the fourth power of the particle's velocity and is significant even for subatomic particles. If we attempted to accelerate massive objects to similar fractions of light speed, the problem would be magnified by many orders of magnitude. The ship would radiate enormous amounts of energy, requiring even more fuel and shielding,
exacerbating the same limitations of energy, propulsion, and structural integrity we have discussed extensively. Accelerators also reveal the practical limits of continuous acceleration. While microscopic particles can be accelerated to near-light speeds over relatively short distances thanks to their negligible mass, macroscopic objects with mass face exponentially increasing resistance in the form of energy requirements. The accelerators demonstrate that relativistic physics is not just theoretical. Even at the scale of subatomic particles, accelerating anything towards c is incredibly energy-intensive. If we extrapolate these results to a spacecraft weighing tons, it becomes clear why even reaching 10% of light speed is considered a massive technological achievement. Accelerators also shed light on how interstellar collisions would affect high-speed travel. Protons and heavier ions in a collider are accelerated in ultra-high vacuum conditions to avoid interactions with stray particles, precisely because even a single collision at near-light speed can release tremendous energy. This mirrors the hazards that a spacecraft would face in the interstellar medium. Microscopic dust and gas that are harmless at low speeds become catastrophic at near light speed velocities, as we discussed in the relativistic energy collision section. Particle accelerators provide a tangible, experimentally verified analog of these hazards on a microscopic scale.
Beyond physics, these experiments highlight the limitations of current technology. Maintaining a particle at near light speed requires massive, highly specialized infrastructure and constant energy input. There is no conceivable method with present technology to extend this principle to objects with appreciable mass. Even theoretical proposals for light sails or antimatter propulsion confront the same fundamental problem. Energy scales, structural stresses, and safety limits grow exponentially as mass increases, demonstrating the chasm between microscopic experimentation and practical spacecraft design. Finally, near-light speed particle experiments provide critical insights into time dilation, relativistic mass, and the dynamics of energy, all of which serve as a cautionary tale for interstellar ambitions. They illustrate that while fundamental physics allows velocities arbitrarily close to light speed for mass-bearing particles in theory, engineering such motion for macroscopic objects remains far beyond reach. The gap between subatomic success and human-scale implementation highlights why current realistic goals focus on fractional light speeds, modest yet achievable fractions of c, which we can hope to reach with future technology. Particle colliders, in essence, give us a laboratory-scale demonstration of the universe's rules. They confirm Einstein's predictions and provide an experimental baseline for understanding relativistic effects. But they also make it abundantly clear why near-light speed travel for humans is a monumental challenge. Every acceleration, every collision, and every energy calculation underscores that while physics allows high-speed motion in principle, our technology and engineering capabilities are orders of magnitude too limited to make near-light speed interstellar travel feasible at present. This naturally leads into discussions of realistic future goals, focusing on achievable fractions of light speed, which remain the most plausible path for human interstellar exploration in the foreseeable future. Given all the staggering obstacles we've explored, from the energy requirements, relativistic mass increase, and interstellar dust hazards, to the fundamental limits of quantum gravity, the dream of traveling at or near the speed of light seems nearly impossible with current technology. However, humanity doesn't have to reach the absolute speed limit to make interstellar travel practical on practical timescales. The concept of fractional light speed travel emerges as the most realistic and actionable path forward. By achieving velocities that are significant fractions of c, such as 10% or 20% of the speed of light, we can dramatically reduce travel times to nearby star systems, without encountering the full brunt of relativistic and engineering constraints that make near-light speed travel so insurmountable. At 10% of the speed of light, a spacecraft could reach Proxima Centauri, our nearest stellar neighbor, in approximately 40 years. At 20%, the journey could be cut roughly in half. While still longer than a typical human lifespan, these speeds place interstellar travel within a conceivable timeframe for human missions, particularly if multiple generations of researchers and engineers plan and monitor unmanned probes.
Reaching these velocities requires immense energy, but they are orders of magnitude more achievable than attempting to approach C. The energy scales, though still challenging, are within the realm of advanced propulsion concepts such as light sails, nuclear fusion drives, or beamed energy systems. One of the most ambitious and widely publicized efforts in this arena is Breakthrough Starshot, a project aiming to send ultra-lightweight, unmanned probes to Alpha Centauri at up to 20% of the speed of light. The project's strategy relies on a fleet of tiny spacecraft, each weighing only a few grams, equipped with light sails that are pushed by powerful Earth-based lasers. By dramatically reducing the mass of the spacecraft, the project mitigates many of the energy and propulsion challenges that plague traditional massive starships. A tiny, gram-scale probe requires far less energy to accelerate and can reach relativistic fractions of c within minutes to hours under intense laser illumination, something completely impossible with conventional spacecraft. The Starshot concept also sidesteps many of the hazards that make near-light-speed travel of massive ships nearly impossible. Tiny probes are less affected by interstellar dust. Even if some are destroyed, the loss is minimal compared to risking an entire human crew. Time dilation is essentially negligible at 20% of light speed, and the structural integrity of the probes can be engineered with cutting-edge materials designed to survive high-speed passage through the sparse interstellar medium. The project exemplifies how focusing on feasible, small-scale missions allows humanity to begin exploring the stars within the constraints of current and near-future technology.
Other propulsion methods for achieving fractional light speeds have been studied in parallel, including fusion-powered spacecraft, where high-efficiency fusion reactions provide continuous thrust over long periods, and ion drives, which offer low but sustained acceleration. While these methods cannot reach 20% of light speed for massive, crewed spacecraft with current technology, they demonstrate that fractional light speed travel is not purely science fiction. The main challenge remains energy density and efficiency, carrying enough fuel and reaction mass for continuous acceleration over decades without exceeding feasible mass-to-thrust ratios. Even a modest fractional speed would represent a monumental leap for humanity. At 10% of light speed, interstellar missions become achievable on a timescale compatible with human lifespans or multi-generational planning. Scientific returns would be extraordinary: direct imaging of exoplanets, measurement of interstellar magnetic fields, analysis of cosmic dust, and the possibility of discovering habitable worlds or signs of life. It also serves as a stepping stone, both technologically and philosophically, toward more ambitious goals. Each incremental advance in propulsion, energy management, and material sciences brings us closer to a future where interstellar travel is not just a theoretical dream, but a tangible reality. Fractional lightspeed missions also offer valuable opportunities to test our understanding of relativistic physics in practice. Even at 10 to 20% of c, relativistic effects like time dilation and length contraction begin to manifest in measurable ways, providing opportunities to refine models and validate theories in ways particle accelerators and Earth-bound experiments cannot. These missions can bridge the gap between theory and practical experience, preparing humanity for progressively faster and more complex interstellar voyages in the centuries to come. Another advantage of focusing on fractional lightspeed travel is the risk mitigation for human missions. Fully relativistic travel involves extreme g-forces, massive energy requirements, and lethal collision risks. By limiting velocities to fractions of light speed, spacecraft can be designed to maximize safety, efficiency, and longevity. Life support systems, shielding, and propulsion do not have to withstand the extreme stresses that would accompany near light-speed travel, making crewed exploration, while still extremely challenging, potentially achievable with sustained research and incremental progress. While Breakthrough Starshot and similar initiatives focus on unmanned probes, their success would lay the technological foundation for larger-scale missions. Lessons in material science, propulsion, laser beaming, navigation, and radiation shielding could eventually translate into spacecraft capable of carrying humans or more sophisticated instrumentation to nearby stars. In essence, achieving 10 to 20% of light speed is not the end goal, but a critical stepping stone toward humanity's long-term interstellar ambitions. Ultimately, fractional lightspeed travel illustrates a key principle. Humanity does not need to break the cosmic speed limit to begin exploring the stars. By accepting realistic velocity constraints, we can make interstellar exploration achievable on human-relevant timescales, while avoiding the insurmountable problems associated with near light-speed travel. It is a pragmatic approach that leverages our current understanding of physics, energy, and engineering, while opening the door to future breakthroughs that may one day allow even faster travel. The excitement of this possibility lies not just in the technical achievement, but in what it represents for humanity's future: the chance to leave our solar system, explore other worlds, and fundamentally expand our understanding of the universe. Even at fractions of light speed, interstellar exploration moves from theoretical speculation to actionable reality, and with it comes the profound potential to reshape our place in the cosmos. This naturally leads to contemplating what such advancements would mean for humanity, not just in scientific terms, but philosophically, culturally, and existentially. Reaching even a fraction of the speed of light would be a watershed moment for humanity, fundamentally altering how we perceive our place in the cosmos. For centuries, the stars have been points of wonder, visible yet untouchable, symbols of aspiration and curiosity. The notion that we could send probes, and eventually humans, to other star systems within a few decades transforms those distant points of light into attractive mysteries, into tangible destinations. A spacecraft traveling at 10 to 20% of light speed could traverse the 4.2 light-years to Proxima Centauri in a human lifetime, meaning that our generation could in principle witness the first human-engineered objects arriving at another star system. This realization would mark the transition from being observers of the universe to active participants in it, with profound implications for science, philosophy, and human identity.
The scientific opportunities would be unprecedented. Even unmanned probes reaching nearby stars could return data that revolutionizes our understanding of exoplanets, interstellar medium, and the dynamics of star systems. Instruments aboard these probes could analyze atmospheres, search for biosignatures, and map planetary surfaces in detail unimaginable from Earth. For the first time, we could gather in situ measurements of a planetary system beyond our own, opening a direct empirical window into worlds that, until now, have existed only as points of light and shadows in telescope images. Each successful mission would exponentially expand our knowledge of physics, chemistry, and potentially even biology on interstellar scales, creating a foundation for future generations to pursue crewed exploration. The philosophical and cultural impact would be equally profound. Humanity has long been defined by its geographic limitations, first the continents, then the oceans, then the solar system. Expanding to other star systems would constitute a leap on a scale previously reserved for mythology and science fiction. It would challenge our understanding of identity, community, and perspective. We would have to grapple with the notion of multi-generational endeavors, where explorers set out on decades-long voyages, fully aware they may never return to see their origins again. The idea of a human presence becomes decoupled from immediacy, emphasizing continuity, planning, and the long-term survival of civilization over the short-term focus of everyday life. In essence, even fractional light-speed travel fosters a mindset that spans generations, encouraging long-term thinking and a broader sense of stewardship for our species and our technology. There are also practical considerations. Fractional light-speed travel, especially for unmanned probes, allows us to test technologies and methodologies that could one day support human interstellar exploration. Lessons learned from laser propulsion, radiation shielding, navigation across light years, and autonomous systems would form the technological foundation for larger crewed missions. Each milestone achieved in fractional light-speed exploration reduces uncertainty and risk, moving interstellar travel from an abstract goal to a progressively achievable reality. By starting with small, high-speed probes, humanity can build experience, infrastructure, and confidence for progressively larger and more ambitious endeavors. Moreover, the psychological and inspirational value cannot be overstated. The success of a spacecraft traveling to another star, even unmanned, would capture the public imagination in ways analogous to the moon landing or deep space exploration within our solar system. It would provide a unifying vision for humanity, inspiring new generations of scientists, engineers, and dreamers. The knowledge that we can reach beyond our solar system within decades would instill a sense of connection to the broader cosmos, fostering curiosity, collaboration, and ambition on a planetary scale. The stars would no longer be unreachable dreams, but real destinations toward which humanity can aspire.
There are also profound existential implications. Reaching other star systems, even at a fraction of light speed, redefines a human understanding of vulnerability and opportunity. We would no longer be confined to a single planetary system, making the survival of our species less dependent on local catastrophes. Interstellar exploration represents a form of insurance for civilization, creating avenues for expansion, colonization, and the long-term survival of human culture, knowledge, and biology. By extending our reach, we increase resilience against existential threats and broaden the horizon of possibilities for future generations. Even modest speeds of 10 to 20% of light speed also confront humanity with the reality of time dilation and communication delay, albeit in a manageable form. While the effects are much less dramatic than near light speed travel, they would still shape mission planning, decision-making, and the autonomy of spacecraft. Crews and probes traveling to nearby stars would need to operate independently to some extent, pioneering autonomous technologies and deep space systems that extend human presence far beyond Earth. These lessons would be invaluable for eventual human missions, enabling long-duration self-sufficient operations in environments vastly different from our home planet. In a sense, fractional light-speed travel represents a bridge between imagination and reality. It is fast enough to make interstellar journeys meaningful within human-relevant timescales, yet slow enough to remain physically and technologically feasible. It transforms the dream of interstellar exploration from a philosophical curiosity into an achievable endeavor, while still honoring the profound challenges posed by physics. Every gram-scale probe or small fast-moving craft becomes a stepping stone, a test of our ingenuity, and a symbol of humanity's desire to reach beyond its immediate surroundings. Ultimately, reaching even a fraction of light speed offers humanity a taste of what it means to be an interstellar species. It allows us to extend our presence beyond the solar system, to explore, learn, and eventually inhabit the stars. It represents a bold commitment to exploration, scientific advancement, and the long-term survival of civilization. The stars once distant and untouchable begin to feel within reach, not as instantaneous journeys, but as attainable destinations whose exploration is possible within decades rather than millennia. In this context, fractional light-speed travel is not merely a technical achievement. It is a profound transformation in human perspective and ambition.
This vision, however, is tempered by humility. The universe will always impose limits, from the speed of light to the hazards of space. But even accepting these boundaries, humanity can chart a course toward the stars, expanding knowledge, preserving civilization, and inspiring generations. The final reflection, then, is one of aspiration tempered by respect for physics. The universe may not allow us to break the speed of light, but it cannot prevent us from reaching for the stars, step by careful step. As we step back and look at the vastness of the cosmos, the challenges of interstellar travel, and the immutable laws of physics that govern it, a profound realization emerges. The speed of light is not just a number, it is a fundamental limit woven into the fabric of reality. Every barrier we have explored, the relativistic mass increase, infinite energy requirements, time dilation, length contraction, deadly interstellar dust, quantum gravitational unknowns, and the hazards of near-light-speed collisions underscores the universe's rigidity in enforcing this cosmic speed limit. Yet within these constraints lies a paradoxically liberating truth. We are not powerless. Human ingenuity, persistence, and creativity are forces that allow us to navigate these limits, even if we cannot transcend them. Fractional light-speed travel exemplifies this spirit. While we may never propel a massive spaceship at the speed of light, reaching 10%, 20%, or even slightly higher fractions is enough to open the stars to exploration within lifetimes. By leveraging advanced propulsion, miniaturized probes, and innovative engineering, we can reach other star systems, gather knowledge, and establish a human presence beyond the solar system. Each mission, however modest in scale, becomes a statement of intent, that we refuse to be confined by our planetary cradle, that we will extend our gaze and presence into the universe, despite the physical limits imposed upon us. There is also a philosophical dimension to this endeavor. The laws of physics, while immutable, do not diminish the human drive to explore. They define the playground in which our ingenuity must operate, shaping the challenges we face and the solutions we create.
Confronting these limits requires not just technical mastery, but vision, perseverance, and imagination, qualities that have propelled humanity from the first navigators crossing oceans to astronauts leaving Earth orbit. Interstellar travel, even at fractional light speeds, represents the next great expression of this enduring impulse. Moreover, the pursuit of the stars fosters a collective mindset of long-term thinking and shared purpose. Generations of scientists, engineers, and explorers must work together to overcome challenges that span decades or even centuries. This requires humility in the face of the universe, patience with the slow pace of experimentation and discovery, and courage to venture into realms that may seem forbidding. It reminds us that exploration is as much about the journey, the questions we ask, the knowledge we gain, and the cooperation we cultivate, as it is about the destination. Even speculative ideas like warp drives and wormholes serve a similar role in human imagination. While they may never materialize, they push the boundaries of what we consider possible, inspire research into exotic physics, and stimulate the creativity necessary to solve seemingly intractable problems. The universe's constraints, therefore, are not limitations on our ambition, but a canvas upon which innovation and curiosity can flourish. Ultimately, the story of interstellar travel is not merely a story of propulsion in physics, it is a story of human aspiration. It is about confronting impossible odds, learning from each incremental achievement, and daring to extend our reach into the unknown. Even when the universe places boundaries that cannot be crossed, the speed of light being the most profound, we find ways to navigate within them, achieving what once seemed impossible through careful planning, incremental progress, and visionary thinking. The universe may not let us break light's speed limit. It may continue to enforce the laws of relativity, the dangers of relativistic collisions, and the mysteries of quantum gravity. But none of these boundaries can stop the human spirit from striving upward and outward. Each probe launched at a fraction of light speed, each experiment in particle physics, each theoretical exploration of space-time is a testament to our determination to explore, understand, and inhabit a universe that is vast, beautiful, and demanding. In the end, what we gain is not merely the ability to reach another star, it is the affirmation that human curiosity, resilience, and imagination are boundless, even when the universe itself imposes strict limits. The cosmos may be governed by immutable laws, but it is our response to those laws, our vision, our ingenuity, and our relentless striving that defines what is truly possible. So while light speed may remain an insurmountable barrier, our reach is not limited by that law. Humanity can probe, explore, and expand into the interstellar void, guided by knowledge, creativity, and perseverance. The stars, once distant and untouchable, begin to feel within reach, not by breaking the rules of the universe, but by learning to navigate them, with patience, ingenuity, and vision. The universe might not let us break light's speed limit, but that won't stop us from reaching for the stars. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.